Murali sir, is my screen visible?
Yes, sir. Visible, sir.
Okay, okay.
Sir, keep the PPT in presentation mode.
Okay, okay. Dear participants, good evening once again and welcome on behalf of Department of ECE NR Institute of Technology. So within 5 minutes, we are going to start the inaugural session. Hopefully, we will wind up the inaugural session by 6:30 p.m. After that, the regular sessions, session 1 and session 2 of today's will continue. In the next 5 minutes, we are going to start the inaugural session.
ఈసారి చూస్తే అస్సలు మిస్ అవ్వరండి.
విఎస్ఆర్ గారు ఎంతమంది జాయిన్ అయ్యారు?
సార్ 84 సార్. గుడ్ ఈవినింగ్ సార్.
ఓకే, గుడ్ ఈవినింగ్. గుడ్ ఈవినింగ్.
గుడ్ ఈవినింగ్ సార్.
గుడ్ ఈవినింగ్ సార్.
గుడ్ ఈవినింగ్ సార్.
గుడ్ ఈవినింగ్ టు వన్ అండ్ ఆల్.
గుడ్ ఈవినింగ్.
విఎస్ఆర్ గారు మొదలు పెట్టేసేయండి. హలో విఎస్ఆర్ గారు.
సార్ ఓకే సార్, ఓకే సార్,
మొదలు పెట్టండి.
ఓకే సార్.
యా.
Dear participants, let us go ahead with the inaugural session. Arpita madam, make it full screen, please. Welcome slide, make it full screen. Yes, right.
Sir, are you recording it?
Yes, sir. I have started recording.
Okay, good.
Okay. Respected dignitaries, resource persons, and dear participants, good evening to all of you. I am Dr. V. Srinivas Rao, Professor of ECE, NRIIT Institute of Technology, and the coordinator for this workshop, for this faculty development program. It's my privilege to welcome you all to this inaugural session of AICTE Training and Learning Academy, that is ATAL Academy sponsored faculty development program on advanced VLSI design and AI-enabled automation for next generation semiconductor manufacturing, organized by our institution, that is NRIIT Institute of Technology, located at Potavarapadu village, Agripalli Mandal, Yelloor district of Andhra Pradesh. This FDP aims to enhance the knowledge and teaching skills of faculty members in line with the latest advancements in the field of VLSI design and semiconductor manufacturing. Through this 6 days program, we intend to foster an environment of collaborative learning, innovation, and practical understanding. We are grateful to AICTE and the ATAL Academy for providing this opportunity to our institution and supporting continuous professional development across the country. I sincerely thank our Honorable Chairman, Dr. R. Venkatrao Garu, beloved Principal, Dr. C. Nagabhaskar Garu, Academic Director, Dr. G. Samsivara Garu, Dean R&D, Dr. K.V. Samsivara Garu, Director Placements, Dr. N.V. Surendra Babu Garu, Head of the Department of ECE, Dr. K. Ramanjanil Garu, and all the eminent speakers who have accepted our invitation to be part of this event. Once again, a warm welcome to all the participants from across India who have shown great enthusiasm in joining us. In fact, in this FDP, there are participants from 17 states across India, and I look forward to a productive and enriching FDP. With these few words, now I would like to invite our beloved principal sir, Dr. C. Nagabhaskar Garu, to address this online gathering.
Okay, thank you, VSR Garu. Ladies and gentlemen, sir, can you hear me?
Yes, sir. Yes, sir. Go ahead.
Ladies and gentlemen, esteemed faculty members and dear participants, I am honored to welcome you all to our 6-day online faculty development program on advanced VLSI design and AI-enabled automation for next-gen semiconductor manufacturing. This program is a testimony to our institution's commitment towards innovation and excellence in education. We are proud to bring together experts, academicians, and researchers to share knowledge, ideas, experiences in this rapidly evolving field. VLSI design and AI-enabled automation are transforming the semiconductor industry as we strive to create more efficient, powerful, and sustainable electronic devices. The role of advanced VLSI design and AI-driven automation becomes increasingly crucial. The demand for skilled professionals who can design, develop, and implement cutting-edge VLSI systems and AI-powered automation solutions is increasing day by day. This program aims to equip you with the knowledge and skills necessary to excel in this rapidly evolving field. Over the next 6 days, this FDP will delve into latest trends and advancements in VLSI design and their applications in semiconductor manufacturing. Expert resource persons from industry, academia will guide you through a range of topics. I believe this FDP explores a latest design methodologies tools and technologies for creating. This FDP going to discuss the applications of AI and ML in semiconductor manufacturing, including predictive maintenance, quality control, and process optimization. This FDP examines the latest developments in VLSI design and AI-enabled automation, including the impact of emerging technologies in quantum computing and the Internet of Things. I expect this program to promote a collaborative learning environment where the participants can share their experiences and also they can interact well by asking questions and engage in meaningful discussions. Before concluding, I would like to express my gratitude to AICTE ATAL Bureau for sanctioning this FDP program to our institution. Every year in our institution, we are conducting 2 to 3 ATAL FDP programs in online or offline mode. This year also, already we conducted one advanced ATAL FDP program by EEE department, and now one program by this ECE department, and one more program by CSE department is in the pipeline. I congratulate the program coordinator, Dr. V. Srinivas Rao, and co-coordinator, Dr. Y. Arpita Madam, for getting sanctioned this FD program. And from last 2 months, they are working hard relentlessly to make this program a grand success. Also, I congratulate head of the department of ECE, Professor Ramanjaneyal Garu, and entire organizing committee members of ECE department for their efforts in making this event grand success. Also, I thank Dr. R. Venkatrao Garu, chairman of our institution, for providing all the necessary resources. I wish you all a productive and enriching experience over the next 6 days that will benefit the society and drive technological progress. Thank you one and all for giving this opportunity. Thank you.
Thank you, sir, for your beautiful words. Now, I would like to invite our Dean R&D, Dr. K.V. Sansura Garu, to provide some insights into regarding this workshop.
Thank you, sir. Good evening, distinguished dignitaries, eminent resource persons, faculty members, and participants. I feel truly honored and privileged to be here with you today at the inaugural session of this 6 days faculty development program, which is sponsored by All India Council of Technical Education and ATAL Academy on advanced VLSI design and AI-enabled automation for next generation semiconductor manufacturing. At the outset, let me place on record my sincere appreciations to the coordinators, Dr. V. Srinivas Rao and Dr. Y. Arpita, and also the head of the department, Dr. K. Ramanjaneyulu, along with his team, dedicated team, for their vision in selecting such a timely and impactful theme and for meticulously organizing this program. Their efforts reflect the true spirit of academic leadership and teamwork. To add to the participants, some of the R&D efforts from our institution. In our institution, NRIIT Institute of Technology, the management is encouraging faculty members to take up the R&D related activities, and it is also supporting with the necessary financial assistances. To your note, I am just presenting some of the statistics of R&D department. The faculty members have published their research papers in international journals of about 417 papers in last 2 years, and about 25 textbooks were written by our faculty members during these 2 years. And patents, recently most of our faculty have filed their patents, and it is the number of 126. Still 50 more patents are under process. And project funding, the institution has got 2.54 crores of rupees during last 5 years for the R&D projects, especially from AICTE, DST, SERB, and other government agencies. So this is our 7th ATAL FDP program. We covered the basic ATAL FDP and also the advanced FDP, and one more ATAL program, that is international conference in regional languages, which is going to be conducted in the month of February. Coming to the conference topic, so we are living in an exciting era where semiconductor technology and artificial intelligence are transforming every dimension of our lives: communication, healthcare, industry, education, and even governance. As India aspires to emerge as global hub in semiconductor design and manufacturing, its initiatives like FDP that prepares our faculty and researchers to play a crucial role in building a self-reliant and innovation-driven nation. I am delighted that this FDP has drawn around 100 plus participants, and there are about 10 plus resource persons. Together, renowned experts from premier institutions, industries, and international universities. Their contributions will not only expand knowledge, but also inspire new ways of thinking in VLSI design, AI-driven automation, and semiconductor manufacturing. To all the participants, faculty colleagues, scholars, and industry professionals, I encourage you to take full advantage of this wonderful opportunity, engage deeply, ask questions, and explore collaborations. Remember, the future technology is not something we wait for, it is something we create together. Once again, I congratulate the organizers for their remarkable efforts, and I wish this 6-day program a grand success. I am confident that the learners and discussions here will lead to innovations that benefit not just academia and industry, but also society at large. So thank you very much, and best wishes to all of you. Thank you.
Thank you, sir. Thank you so much for providing the detailed report about our R&D work at our institution. Now, let us listen from our placements director, Dr. N.V. Surendra Babu garu.
Very good evening, one and all. It's a pleasure to be a part of this wonderful ATAL FDP in this evening. NRI known for the upliftment of the faculty to the latest technologies. In this connection, the 7th FDP of online conducted by the Department of ECE on VLSI design will be a great success, and a lot of inputs in the next week will be make sure that the students and the faculty will be benefited from this particular things. I wish you the best of luck for the organizers for providing this opportunity. Thank you.
Thank you, sir. Now, I would like to invite our respected head of the department, Dr. K. Ramanjanil garu, to speak few words.
Good evening to all of you. Respected Principal Sir, Academic Director, Dean R&D, Director Placements, Coordinators, our distinguished guest, Dr. Avatar Singh, faculty colleagues, and my dear participants. It gives me immense pleasure to address you all on the occasion of the inaugural session of this 6-day online ATAL Faculty Development Program on Advanced VLSI Design and AI-enabled automation for next generation semiconductor manufacturing, organized by the Department of ECE at NRI Institute of Technology, Agirpalli, Vijayawada. At the outset, I extend my heartfelt gratitude to AICTE ATAL Academy for sponsoring this FDP and for constantly empowering faculty across the country through their visionary training initiatives. The theme of this FDP is both timely and futuristic. Today, the global semiconductor industry is witnessing unprecedented growth driven by demands in AI, IoT, 5G, and high performance computing. At the heart of this revolution lies VLSI design, where innovation in design methodologies and automation tools is essential for building next generation chips. Equally important is the role of artificial intelligence in semiconductor manufacturing. From process optimization and yield improvement to predictive maintenance and design automation. AI is transforming traditional practices into intelligent data-driven solutions. This convergence of VLSI and AI-enabled automation will pave the way for sustainable, efficient, and scalable semiconductor technologies, crucial for India's vision of becoming self-reliant in electronics and semiconductor manufacturing. I am confident that this FDP will provide participants with a deep understanding of advanced VLSI design concepts, explore to AI-driven automation tools and applications, and insights from distinguished resource persons who are experts in this domain. Not only enhance faculty competencies, but also translate into better teaching learning outcomes for our students, making them industry ready and globally competitive. On behalf of the Department of ECE, I warmly welcome all the participants who have joined from different parts of the country. I encourage each one of you to actively engage, interact, and utilize this unique learning opportunity to its fullest. Before I conclude, I would like to appreciate the dedicated efforts of the coordinators, Dr. V. Srinivas Rao and Arpita Madam, organizing team, and management of NRI Institute of Technology for their continuous support in making this FDP possible. Let us look forward to 6 days of knowledge sharing, collaboration, and innovation that will certainly enrich all of us. Thank you very much for giving me this opportunity.
Thank you, sir. Thank you so much. Now, before I invite our special guest of this inaugural session, Dr. Avatar Singh, sir, Professor of ECE, Adama Science and Technology University from Ethiopia, I would like to invite our co-coordinator, Dr. Y. Arpita Madam, to briefly introduce sir to this meeting.
Respected dignitaries, esteemed guests, and dear participants, myself, Dr. Y. Arpita, co-coordinator of this FDP, would like to extend a very warm and cordial welcome to each one of you to this faculty development program sponsored by AICT ATAL Academy. It gives me immense pleasure to welcome such an enthusiastic and diverse group of participants who are committed to continuous learning and professional development. We are deeply honored to have with us our special guest and keynote speaker, Dr. Avatar Singh, sir, a distinguished academician and expert in this field. Sir, your presence here is truly inspiring, and we are grateful for your time and willingness to share your valuable thoughts with us. Love. So it's my privilege to introduce Dr. Avatar Singh, sir. Avatar Singh is a seasoned academician and VLSI specialist with over 15 years of experience in teaching, research, and university administration. He has published more than 70 research articles in reputed journals and conferences, contributing significantly to the advancement of semiconductor and VLSI design. His scholarly work spans SEI and Scopus Index platforms, and he has delivered over 40 expert talks across India and internationally. His overseas contributions include serving as an associate professor in the Department of Electronics and Communication Engineering at Adama Institute of Science and Technology University, Ethiopia, where he led academic initiatives and mentored educators on innovative teaching strategies. A senior IEEE member and reviewer for leading journals such as IEEE Access, JSS, ECS, and Silicon, Dr. Avatar Singh sir specializes in postgraduate mentorship, curriculum innovation, and academic development. His career includes key roles at NIT Silchar, C.V. Raman College of Engineering, Invertis University, and JIS University with notable achievements in accreditation, leadership, and global outreach. So now I request our special guest and keynote speaker for today's session, Dr. Avatar Singh sir, to hand over the session.
Hello, I'm audible, sir?
Yes, sir. Audible, sir.
Yeah, okay. So thank you for providing me an opportunity
to just give my thoughts on the VLSI. Although, as we already know, that this is a great thing that we are going to start with the VLSI nowadays. As you already know that the government also planned around 76,000 crore of budget. Definitely, if we have a good setup for the VLSI, including the faculties and the labs, then we can supervise the students very well, right? So this is like what we are looking for now in nowadays, right? So just I'm going to start.
Dear participants, please mute your mic.
K. Varaprasad garu, please mute your mic.
Murli sir,
All participants, please.
Please mute all. Murli sir, please mute all. Then Avatar Singh sir, you please unmute yourself.
Okay, now it's okay, sir.
Yes, sir. Yes, sir. Good.
How do I have to share the slides in this? I'm not getting any point. Might be you have not given me authority, something like this.
No, sir. You have been given the presenter option, sir. Just
Okay.
beside the camera and mic option, there is a share option, sir. On the right top corner of your laptop.
I got it, sir.
From there, you can share the screen.
Share screen with audio, without audio. I think without audio, right? Because audio is coming. With audio.
With audio.
With audio.
Hello.
Okay.
Huh?
My screen is shared, sir.
It is being shared, sir.
Okay, that's great. It's fine, right?
Okay, sir. Avatar Singh, sir, small request.
Yeah, please.
Sir, before we proceed with your session 1, I request all the dignitaries and resource persons and my dear participants, please switch on your cameras for a snapshot, sir, please. All of you, please on your cameras. All the participants. Avatar Singh, sir, please stop your share screen so that we can capture the camera screenshot.
Yeah,
please stop your share screen.
Yeah, I'm not getting the option how to stop. So you can stop from your side. Please make it. I'm not getting the option actually.
Okay, sir. Arpita, madam.
Sir.
Please take screenshots.
Where is the option, sir? You
Hello,
can stop my
sir.
Sir.
You can create a gallery and you can take that.
Sorry, sir.
You can create a gallery. Just show the view option. There is a gallery option. So large gallery you can create, and where people are sitting in various seats, you can find out.
Okay.
Or together mode. It is together mode.
Arpita, madam, please do it as sir has suggested. As sir has suggesting, please do it. We will take a snapshot and then proceed with session 1.
Yeah. I'm not getting where is the option.
Murli, sir.
Sir, you can take a screenshot here.
Murli, sir, please look into it. Please look into it.
Sir.
As Dean sir is suggesting for a
together mode. Go to view option, identify together mode, you find gallery.
Together mode. Large gallery is there, I think, sir.
Yeah, together mode. Just go for together mode.
Yes, sir. Yes, sir. Got it, sir.
Arpita madam, take screenshot
Yes,
of this current view also with
yes, sir.
starting slide of Avatar sir, Avatar Singh sir.
Already I've taken, sir.
Murali sir, okay na?
Okay, sir.
Okay, sir.
Have you taken the
Hello.
sir?
Yes, sir.
Just 1 minute, sir. Just one more
Okay.
minute, sir.
No,
They
no
are
problem.
capturing.
No problem. Even I am not getting any option, sir. I don't know.
They are trying to take a photo, sir, screenshot.
Okay, okay. I will open the slide then.
Yeah, you can open your starting slide, sir. Okay, okay, sir. It is visible.
Okay, VS sir, you continue the program.
Okay, sir.
Okay, right.
Murali sir, if you say okay, then we'll go ahead with session 1.
Okay, sir. Okay.
Yourself or Arpita ma'am.
Okay, sir. Okay, sir.
Sir, continue, sir.
So shall we continue?
Yes, sir.
Yes, sir.
Shall I start?
Yes, sir. Yes, sir. Avatar Singh, sir, please continue, sir.
Okay. So as we have already, thank you for participating and thank you NRI College to invite me to just share my thoughts on like something like what I am doing in research and semiconductors basically. So what I'm saying, because we all are teachers now, FDP is basically for faculty development. So as we have already knows that like there is some admissions and all those things in computer sciences somehow, but as per the current budget scenario, so I'm putting first slide, I'm putting the budget scenario, which makes us happy because might be after if you are working in VLSI, so definitely up to 2030 there are huge demand of the teachers as well as engineers as well as fabricate, means whatever the things related to VLSI, everything is in demand and more than that of like any other branch, because as we have already knows, this is the budget what the government has given every year. Okay, so just if you see total budget allocation, if we see in year 2023 3,000 crore, then in 2024 it becomes 6,903 crore, 2025 it's 7,000 crore. Out of that, 1,000 for semiconductor fabrication laboratory, then 1,800 for compound semiconductors, and 200 for design linked incentive. Then again in 2024 for CMOS fabs, for compound semiconductors, for Mohali might be, there is a one lab in the Mohali semiconductor SCL, Mohali semiconductor lab actually basically, and then design link incentive 200. Then in 2025 we see 2,500 for semiconductor fabs, 3,900 for compound semiconductors, ATMP and OSAT, then 200 for design linked incentives. And if we see the time frame like estimated jobs, so already if we see the 2030 vision, so around 8 to 10 lakh jobs is required, because definitely if the government is invested this much of a money, so definitely in India we need like the workforce. So from where we are getting the workforce. So that's why VLSI now, if we are moving all the branch, like even you are means VLSI is also very wide. As you are already teachers, so you already know there is a VLSI devices, there is a VLSI circuits, then there is a we are doing on the back end, front end, then interconnect engineers, then physical layout engineers, physical design engineers, then test engineers, then developers who are working on VHDL, Verilog type of a thing, then the person who are working on the analog VLSI designer, digital VLSI designer, mixed signal VLSI designer. So everything is in the boom, believe me, because like what we predict, because everyone needs, because if we have started the fabrication of the chips in India, so then we need everyone. Till now, what we are doing in India, basically, what I know is, then we are just making that like layout up to layout, and then we are going it to, we are giving it to somewhere, and then the persons are doing the same things there, right? So these type of things generally we are doing, right? But might be after when we have the fabrication facility, definitely we have a more work and we need more workforce. Okay, so we have to supervise our students accordingly, like what skills they required. Like, because if we are working with the conventional skills, believe me, it's not possible to finish the things. Because if you are starting from the transistors, BJT, then we have one syllabus for one course for the BJT. We have to, already the many courses are already changed, but we have to provide skills to our students. This is the major requirement for the time. So, although my topic is just TFET, some novel TFET structures I have to discuss, design analysis of novel TFET structures for low power application. But yeah, in future, if you need some some of time, so we can do like establishment of lab, like VHDL Verilog, then TCAT lab, then circuit lab, whatever the things we can. Okay, because this is the need of the time. Okay, so already I discussed something about the like skill needed, VLSI design, Verilog, VHDL, semiconductor physics and materials, clean room protocols and lithography, AI ML integration in chip design, nanoelectronics and photonics. These things we require. So as just brief history, we know already everyone that we have vacuum tubes in around 20th century. If you see the TV, like old TV, we have seen like some screen is there, big screen. Okay, and then we are getting like a conical type of a structure. Then there is a vacuum tube. Then the electrons are bombarded on the screen. Then we are getting some, due to the recombination of the charges, we are getting some like light. So then we are using the sulfur or phosphorus type of a some photo detector material, photo type of a material. Then we are getting some colors also. So these things we are using. But nowadays the technology is totally different. Okay, but the basic is same. We can't say that if you are working in because when we have to do the research, again we have to come to the basics. How we have started. Research means search again, right? So search. There is a node and for that one. Because if we have to continue the Moore's law, we will discuss about the Moore's law and all those things. So if we have to continue the Moore's law, there is a always, because this is only the motivation behind all the research. So vacuum tubes in 20th century it came. Then 1947 first point contact transistor come. This 3-terminal device, as we have already seen, this is the device, right? So as we know, this is the point contact transistor. If everybody can see, I think. So you see, this is the contact. That's why it's a point contact. Okay, and what we are doing actually, if we are talking about how the MOSFET is working, so we are controlling the flow of charge carriers from source to drain, right? By applying the gate, means electric field on the gate. Basically, this is the voltage control device, and we know V is directly proportional to E, right? So that's why the things are coming like this. So this is the first step of a transistors, what the researchers made in 1947 around. Then 1958, first integrated circuit came. This is made by Jack Kilby, okay, at Texas Instruments, and he got the Nobel Prize. We already know that Kilby's ICs is known as. So this type of flip flop, I think he made flip flop between two transistors that time. Okay. So after that, first planar IC. Planar means we are making on some plane. Okay, if you see, this is not the planar IC, but this is the planar IC. Means we are getting all the things on the plane. So this is the first planar IC. Then 2003, we are getting 55 million transistors in Intel Pentium 4. Then 512 megabit DRAM. It contains 0.5 billion transistors. Then 53% compound annual growth rate over 45 years. If we see, and now this is more than 75% in a semiconductor factory. The whole go, because everything depends on the processor. Now NVIDIA, if there is a no NVIDIA, there is a no AI. Like they made like this. Because this is only we need some chip to run the AI programs. We need some hardware to do some machine learning. So hardware, from where the hardware will come? The hardware will come only from the VLSI, right? So there is we can't say that this is, but yeah, we need, because most of the things are going to be automated. So now this is the challenge for us. Automated, so we have to learn that process, then we have to work. right? Like suppose like I'm working in one university now. So now the chat GPT, everybody is saying chat GPT, stop chat GPT. Some means many type of feelings are coming on the chat GPT. Now think, if we don't know chat GPT, how we control the chat GPT? So for controlling someone, we have to know, and we have to know more than the students. Then we can only able to control. So these are the things, like the same thing, like we have to work hard to get the things run smoothly. So this is what we are doing. Actually, we are just trying to miniaturize the transistor. This is our basic work, right? Scaling, as you already know, you are already a teacher. So scaling is the technology, means this is the method by which we are going to reduce the size of the transistor. Okay, so we are just try to, because our major target is reduction in the area and increase in the speed, means current has to be high and area has to be low. This is our target as a VLSI designer. Always we have to minimize the area and we have to maximize the speed, but there are a lot of constraints are there, because if we are increasing the speed, like suppose if you are moving on the road, right, and more number of cars or bikes are moving on the road, so definitely the number of collisions, mean number of accidents are more, right? Same thing happen in the electrons. If more number of charge carriers are moving with higher speed, current is basically, speed is the current. We know current is speed, just speed. This is analogy we can use. All already teachers, you know all those things. Like speed is a current. So when the vehicle is moving very on the high speed, the like probability of collisions are maximum. So this is the thing. So when we are like decreasing the size, then the collisions are more, increasing the, so these are the constraint type of thing. Because if we have to move freely, mobility has to be more, then what we have to do, the road is free, we should be not like no resistance is there, means there is a no barriers, like we have to move smoothly. So these type of things we have to do. So as a VLSI designer, always two things we have to note: we have to reduce the area and we have to maximize the current. So smaller is cheaper, faster, lower in power. We already know these things. So MOS integrated circuits. So first 1970s only NMOS transistor came. Then 1980s and up to present we are getting CMOS process. Low for low idle power, right? Why we are using CMOS? As we have already know, when we are talking about CMOS, so only one transistor is working at a time. We know, right? Everybody knows. So this VLSI is depend on this only. There is a current is there, but it is short circuit current and it is coming for very small time, right? When the both transistors are in saturation. So on like when we make like in this region only. Okay, else here the transistors are in either in cutoff or either in, means somehow the transistor is not working. Only one transistor is working. Okay, so that's why we are getting the less power in the CMOS technology, and 1980s up to present CMOS processes for low idle power. Now past transistor, dynamic logics, many things are came, but still CMOS is very reliable. If you see 7-4 ICs, basically this is like TTL, and 5-4 is even like this is not our topic. Okay, so this is the Intel 256-bit SRAM, Intel 4004 4-bit, like right. So you see before how they are putting the thing, because this is not the SMD, like they are making like this. So that time, okay. And if you see, this is the simple MOS, like how we are controlling the flow of data, we are controlling the flow of charge carriers from source to drain using this gate, right? If we are moving it in anti-clockwise, then or clockwise, then the speed is increasing, mean more number of charge carrier barrier is decreasing, right? But if we are making in a clockwise, then what happened? The opposite has to be. Means anything can be possible, right? So we are controlling the flow of charge carriers from source to drain using the gate voltage or applied gate current, right? So this is the driving force for everything nowadays, because we have some control switch. If we are talking about diode, one direction is coming, we are stopping in one direction, but here we can control, although this is also one direction, but here what the thing is there, we can control when we have to flow, when we have not to flow. Okay, so that's why this is automatic type of a switch, we can say. So this is the simple thing: gate, drain, source. So we are controlling, and this is the structure of the MOSFET. So here we have source, here we have drain, here we have gate. So we are controlling the gate, and the charge carriers are flowing in this way, right? This is the symbol of the NMOS, right? And this is the IDVG characteristic. This is known as transconductance characteristics. Actually, why we are calling it transconductance? Because we have taken the readings among IDS versus VGS. IDS versus VGS. So one quantity belongs to output, one quantity belongs to input. So IDS upon VGS, if you see, one quantity belongs to output, one quantity belongs to input. And transconductance, why? Because conductance, why? Because I upon V. If V upon I, definitely it's a resistance set. It's very small basic things. Everybody knows already. Okay, so this is the very important like SSVR, because this is the switching speed we are defining here. If this is ideally, it has to be like this, but it is not possible. So it is like little like this, and it should be in the case of MOSFET, we can't make it less than 60 millivolt per decade. Less than, why? Because of the Boltzmann like there is approximation, right? There is a KT by Q, something is there. We will discuss, might be the time will permit. Okay. So due to that one, and then tunnel fed, if we are moving, because our topic is tunnel fed, when we are moving tunnel fed, so we can make it below 60 millivolt per decade. Okay, 60 millivolt per decade. Why I'm saying millivolt means this axis and decade is this axis, right? So this is actually the slope is the inverse of this. Inverse slope is subthreshold swing, and we are talking about subthreshold swing, which should be millivolt per decade. There is a one like question is raising in this. This is slope line mx plus c, we know y equals to mx plus c. So we have to calculate that one. So this is log id current. This is millivolt. So this is an id mean this is, we can say decade, because this is the logarithmic scale we have taken, and this is the millivolt. So if we take like this, so decade per millivolt. Now if we take the inverse of this, it comes millivolt per decade. So this is known as subthreshold swing, which is important, right? And this is defines the switching speed of the device. Okay. So this is the bulk MOSFET, as we have already know. So this is the equation. This equation is coming with the square law method. So already giving in the Kang book. This is the best book. What I means because we are teaching, we are teachers. We should know the book. So Kang, there is a one book. So up to 5 chapters. Everyone, at least every VLSI designer, every VLSI students have to do. If you want to develop some skills in your students, so we will discuss on that one might be. So this is drain current in MOSFET. So this is the saturation case. Right, on operation, and this case off operation. Off means leakage is going on. Okay, high on why? When the length is on or length is high, gate capacitance is high, and VDD minus VTH is actually the gate overdrive voltage. Why we are saying gate overdrive? Because suppose the voltage is giving VT. So first we have to, because we will discuss the simple working of the MOSFET. We will try to discuss. Okay, so high ion L COX VDD minus VTH, and this is VTH low I off, and this is subthreshold swing is also. Now scaling and Moore's law. So number of component, this is very important because this is basically the driving force behind everything. Like whatever, because in 1965 when Moore's law came, the transistor size in micrometers. Now if you see the transistor size is 1.6, 1.4 nano, 1.2 nanometer. 1.2 nanometer. You just think. Means we are working in the Armstrong. This is not the Armstrong scale now. Armstrong. You know Armstrong. This is the electrons sky. Already this is came. I will show you the slide. I have one slide. We will discuss about the technology node and all those things. So what Moore's law said? Moore's law said that in every 1.5 years, or somewhere it's written 2 years, the number of components in the chip should be double. Means if it is 2 million now after 2 years, so 1.5, it should be 4 millions. But the chip size should not be increased, or we can say the number of components should be same, right? But the chip size is going to be half. So this is the Moore's law. In April 19, he has given this law. Okay, and he's also one of the co-founder of the Intel. So Moore's law, transistors count had doubled every 20. Actually, it is 18 months, 24 months, not 26. Okay, so this is, if you see, this is the thing, like the things in 1970. This is the count. This is the count. Then if you see, the number of things are increasing. Now this is the count. Okay, integration level, we know SSI, MSI, LSI, VLSI. Okay, now this, if you see, this is the Pentium 4 processor. See, this is just like a building, you know, just like a building. All the engineers is required, civil engineer, mechanic. Like when you are making your home building, right? You need architect. You need architect. Why? You need architect to make the plan for the building. Before making the building, you need some plan. You need some map. Then you can estimate the cost, like how many bricks are coming, how many days, how many labor for the the person who are fixing the bricks and all those things. Everything you make. Then how many electric lines are there, electric wires are there. Everything before making the building, you have the cost. Same thing when we are making the chip, all the cost is going to be completed before the things. That this is the layout. Generally, this is the map of the chip. Right. After that, we are going with the chip. Okay. So this is the Pentium 4 processor. And if you see, modern transistors are like few micron wide and approximately 0.1 micron or less in length. Modern transistor is very less, right? So human hair is 18 to 90 micrometer in microns in diameter. If you see one human hair on the tip, you see this is also 80 to 90 micrometers. It's very big comparable to the current transistors what we are using. Like we are using 3 nanometer of transistors. We are using 4 nanometer of transistors. Even if you see Apple iPhone 16, it uses 3 nanometer of transistor and it contains more than 19 billions of transistors. It is not less. 19 billions. If you are going to count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it will take around 21 years to count 19 billion. Just imagine. Means counting is like this, and the researchers have already made this much of a transistors in a small chip. So how come it is possible? Like if they can't able to count, means if there is some problem come, so how they will find the problem? This is the big thing. Which transistor is getting the problem? But they have the skills. They have made the skills. So how they made? You know, this is just like out of imaginations. Right? How the things are going to be like 3 nanometer, how they check the transistor 3 nanometer, how they replace the transistor, how the things are going on. Means there is a like big like 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 some magical things are going on. If I am thinking in my mind 19 billion transistors and they are connected together and they are making one circuit and they are working fine. Okay, and more than, and they are working fine not for the single moment, they are working for the like number of years. So how come it is possible? Let's just think. So this is the research we can say, and it comes only due to research. Like we are doing the search again, problem we are finding, we are making the solutions, we are making the problem, we are making the solutions. So problem solutions, and now this situation came, and still the things are going on. Like even now the biotechnology is in your, now you know something are coming like edible electronics. You can eat the food, right? And they will, like by eating the food, the whole body diagnose will come. No need for going to any for some something for like what we say MRI, and this only eating the food they will diagnose the disease. And if the nutrition is less, they are giving the electronics to do these things, because our bodies also have current is there. If you see 0.07 millivolt, there's a resistance. If you see this skin has resistance little bit more, but the around 1000 ohm, something like 1 kilo ohm or 10,000 ohm, something like very, and depends on the skin to skin. And also there is the inner tissues are there that has very less like in ohms. So the things are there, like no, the current is also flowing in our body, right? Because current is what I already told you. Current means speed. So the charge carriers, if you see our heart, there is N plus Cl minus. If you remember, might be if somebody have a high blood pressure and low blood pressure, so the doctor is saying no need to take the salt, right? To take more salt. So what happens actually? Na plus Cl minus. This is only the magic. Many things are there in the word. If you see, and even if you see the, if you just notice it, most of the blood shoot case like high BP and low BP are coming usually during the full moon and no moon. So this is not the like some superstitious thing. This is all are the like physics basically. It works on the gravitational force, right? Because the moon, sun, and earth is on the same line. Some perpendicular, something is there. So there is, everything is science. We are making it okay. That is also important, but like everything have a reason. Okay, so this is the LG scaling path. So we already know 10 nanometer in 19. This is in some nanometers here. Now we are working in 2020, less than 10 nanometer. Now 3 nanometer already iPhone 16, whatever the model are coming, they are coming in 3 nanometers. So in digital circuits, MOS transistor are electrically controlled switch. As we know, if we see this thing, so these are the like gate. Okay, and if drain to source, it is connected. Okay, if G equals to 0, then it is not connected. Right, it is not connected. But if G equals to 1, then it is, in the case of NMOS, connected together. Right, so the signals are coming like this. But if it is not connected. There are high impedance cross them. There is some, like how we are using the transistor is also depend, but this is the simple logic. But in the case of PMOS, the things are totally different. When it is now at 0, it is connected, and at 1, it is not connected. So in the case of PMOS, the things are totally different. But in the case of NMOS, the things are totally different. So CMOS inverter, as we have already knows. So CMOS inverter, if we see, this is A, and we know so this is, we are getting the output, and just basic thing is there. When we have to take the output, we have to take from the drain. And the PMOS source is always at higher potential, the NMOS source is always at lower potential, and the output is always from drain, whatever the case. Okay, so this is the simple CMOS inverter. We know this is the output. How we are getting? Just simple thing. Like suppose we are taking the output from here. So suppose there is one capacitor here. So first time it's going to be charged. So we are not, because we are not getting the direct path here. The circuit is not complete. Another time is going to be discharged. So when it is going to be charged, so this node, how much voltage VDD? Because this transistor is on, this transistor is off at 0. Same thing when this transistor, when we are applying 1, this transistor is on, this is off. So what happened? There is a discharge of the charge carriers from this capacitor. Now this passes wrong. So the things are going ground. So we are getting. This is a simple logic how the CMOS inverter and all those things are working. So we have already knows these things. So I'm not investing much time on this. Again, this is CMOS inverter. So now if we see the CMOS NAND gate, how it works. I don't know what happened to the slides. Something's happened. I don't know. Because it's not like this. I make the figures here also, but okay. Sorry. I have to make the NAND gate. So this is the NAND gate as we already know, and we are taking the output from here. So how it works, suppose the current are coming here. So if we are applying 0, 0, so these both transistors are on, right? So the output is coming here. So it is fun. Both transistors are on now, if 0, 0. Now either 0, 1 is connected, means if it is connected, it is off. Still we are getting one path. So it is at both conditions, it is 1. But when both are 1, means this is connected and there is a no charge. So capacitor is here, it's storing the charge. Now there is a discharge. So this is NAND gate. We know already this is the table for NAND gate. And there is analogy with the water size also in CMOS NAND gate. So this is just how the CMOS NAND gate is working. This is what I have already told you, 4 cycles. So if we see in year 1949, first transistor was made in Bell's laboratory. So it was equivalent to the dimension of the handspun. Then iPhone X, it came in around 2017, if I'm not wrong, 16 or 17. So A11%, now A16 we are using. So it contains the, like the area is only 89.23 millimeter square of space and using a technology of 10 nanometer. And generally we are utilizing the FinFET process. Now what is the FinFET process actually? FinFET means nothing, like you know the fish. So fish, this is the fish, right? So fish control the flow means flow of swimming. We can say by controlling these 3 things, 1, 2, 3. Control the their directions using this 3, and we are saying it fins. So that's why it is known as FinFET, because in FinFET we have controlling from 3 sides, not from 4 sides. So although we are nowadays we are using only not FinFETs itself, we are using the We are not using we are using gate all around FRITs nowadays. Okay, so the things are like this. We will discuss later on. The structural parts also we have like Z shape, U shape, H shape. If the time permits, we will use everything. Okay, so if we will look to our single hair, then its dimension is in micrometer. So it can be said that one single hair contains more than 1,000 of transistors, if I'm not wrong, right? Because we are using in 3 nanometers. 3 nanometer means this is very small, and 1 micrometer means our hair is in some micrometers. So just imagine how many transistors are coming in one, right? So it's more than 10,000, 1,000 around. So this is the whole digital evolution defines in a nutshell. So at the root of this digital environment, there is a tri-terminal switch. There is a one switch, like, or we have already seen the switch, like source, drain, and gate, that makes themselves on off more than that of billion times in a time span of a single second. Just imagine billion times in a single second. Even trillions calculations are going on in a single second. This is the whole evolution, we can say, like what from where we have started and now where we came, means our things are how much fast. Even it's just comparable to the human brain, if I'm not wrong, right? So when we are doing the, because our topic is, this is only the framework I have made just to understand the VLSI. So for VLSI, the major thing is a MOSFET. And what we are doing by scaling, we are reducing the size of the MOSFET. This is the requirement. We are reducing the size of the MOSFET. Now there are two types of scaling. One is known as full like scaling. It is also known as electric field. We are not like going to change the electric field in this internal electric field in this type of a scaling. And one type of a scaling is known as voltage scaling. And that's when we are not going to change the voltages. So there are some, but nowadays we are using only hybrid type of a scaling. We are not using full scaling as well. We are not using. We are using some hybrid type of thing. But when we are reducing the size of the transistor, like suppose the transistor size is like some 1 micrometer. This is the length actually. When we are talking about the transistor size, so this is the length. We are talking about the length. Now this length is very small. It's the nanometer. So definitely this, because how the transistors work, we already know. Just one small introduction I will give. We are controlling the flow of charge carriers from source to drain using applied electric field at the gate. Now, what happened when we are applying here VDS, because this is the VGS component. VGS component, okay, we are controlling somehow. But when we are applying the VDS, so here we are applying the positive voltage, and this is N plus region because we are working with the NMOS, whatever the things. And this is connected with here. This is substrate is connected with the source. This is also a lower potential. This is also a lower potential. So it is reverse bias. Now this diode is getting reverse bias. Now reverse bias, what happens? The depletion region is going to be zero, and it is more in the region, like in the region where we have less doping. If we have more doping, then it is less. As we know that there is a, suppose there is a war is going on between Israel and Palestine. Let's suppose, I'm not in favor of anyone, just for an idea. Like suppose, what you think? Who will penetrate more? Definitely Israel, because it has more charge carriers, it has more support, it has more, more space and more advanced military, whatever the things. So it more spread. Same thing here, right? Same thing, because it has less charge carriers, that has more charge carriers. Same thing. Okay. So like this, and when this depletion region is increasing, whatever our channel is going to be vanish. Due to which, ideally, what has to be happen? The things are going like this, but it's not happening because of some reasons. Because there is a one like tunnel is going to be formed, so our charge carriers will go like this. If you have read the Kang book, you know this, right? So this is known as current mirror. Means we are using the MOSFET as the current source or current mirror here, and here we are using as a resistor. So linear region and saturation. If we already know, we are already just. But when we are going to minimize the size of the transistor, then some special type of effects are coming into existence. These are known as short channel effects. So the main drives for reducing the size of the transistors, their length is increasing speed and reducing cost. Because we need minimum space, maximum speed. This is our target always. So when you make circuits smaller, their capacitance reduce. Definitely. Because what we know capacitance equals epsilon A by D. A is reduced, capacitance is going to be reduced, right? Their length is increasing, speed and reduce, sorry, the capacitance thereby increasing operating speed. Like when capacitance reduces, definitely the speed is going to be more. So however, with great reduction come great problems. So in this came the form of unwanted side effects known as short channel effects are coming into existence. Right. So when the channel of the MOSFET becomes the same order of magnitude as that, this is given in the CAG. I have taken from the CAG. Okay. CAG chapter number 5. If you read, you will find this definition. So when the channel of the MOSFET becomes the same order of magnitude as the depletion layer, width of source and drain combined, when we add this, so the transistors start behaving differently, which impacts performance, models, and reliability. These effects can be divided among the following. So this, when the channel is like equivalent to the depletion region, so that's why the problem is coming. So there are drain-induced barrier lowering, there is surface scattering, there is velocity saturation, there is impact ionization, and there is a hot carrier injection. Although there is a velocity saturation is also there, there is many other punch through, many other short effects are also there, but we are not, because it's not possible to cover everything in a single lecture, right? So first we are just small thing we will discuss, and we will try to finish all the things. So I think already half time we have already finished. Okay, so we have to finish everything. So just I will try to make it fast. And if you have any question, you can ask me in between also, at the last also, as you wish. I will try my best to answer it. So drain-induced barrier lowering. What is drain-induced barrier lowering? What happened? Like suppose this is source and this is gate and this is drain. Like this is when we have, sorry, when we have nothing, so it is like this. But what happened when we are applying, sorry, it is like this, right? Okay, like channel connection band balance, whatever we want to make. So when we are applying the voltage here, definitely we are applying some VDS here. VGS is also there. So VGS is generally is because we know that the VT is the component of the VGS. We don't know that the VT is also the component of the VDS. Although we don't want it, that VDS means drain to source voltage, will control the VT, but it is going to be controlled because of the reduction of the size. Now what happened? When we are applying here voltage, this barrier is going to be like this. Right? This is the MOSFET, and we have made one diagram for the MOSFET. Like this is the band diagram, you can see. Like just roughly idea. So just see, the barrier is going to be lower. So that's why we have said drain induced. Because of drain, barrier is going to be lower. That's why drain induced barrier lower. Right? The area, and then what happened? Due to which the VT is going to be, like VT is going to be changed. Because before what we know, that the VT is the function of the VGS only, but now the VT is also the function of the VDS. So this is the region. So this is just, I told you just all things in the just next, like very small. So this is a plea called drain induced barrier lowering. So like this is going to be done. So for this region, potential barrier is controlled by both VGS and VDS. Although what we believe from the conventional studies, that VT is only controlled by the VGS, but here both. So if drain voltage increases, barrier in the channel decreases, leading to DI. Okay, so allows electron flows from between S and 2 even at low voltage, because the now VT is going to be low. You just think, okay, there is a one family. Okay, so father is only earning, right? So there is some threshold cost of the family. Threshold cost from the means you have to pay the electricity bill. You have to pay the, so suppose the father's salary is around 100,000. So he is spending every month 50,000 to the family. Now what happens? Son is grown and son is also contributed there. Okay, so son is contributed. Now the father, what father is spending on the family, now it's reduced. Because the something is coming from the son's family. Although he is not like, but reduce, because he is also contributing. So the same thing here. Before the everything depends on the VGS, but now VDS when we have applied, then it is also contributing. Now the VT is going to be reduced. This is the reason. Okay, might be the example is a little bit different. What is coming into mind, I have just speak. Okay. So as channel length decreases, the barrier 5B to be surmounted by an electron from the source on its way to the drain reduces. Now it's moving towards the source. So the drain is close enough to the source to easily form the depletion region normally created by the gate. That is, the drain depletion region extends to the source, forming a unique depletion. This is known as, now what happens? Now this is only what we know. This is only we know. Now what happened when sometimes what happened? below, because depletion region is going to be cross here. You know, this is known as punch through. Actually, this is type of a tunneling. We will discuss. This is type of a tunneling. This is also Zener diode is actually the tunneling, right? Zener diode, and it is first it was recognized by the Zener that we have given the recognition tag. But Zener diode is also one of the tunnel diode. It means like we can say that like controllable tunneling. Tunnel diode is also there, but we are not using the negative resistance property in the tunnel diode. Oh, sorry, in the Zener diode. We are using only the breakdown conditions there. So there is a something. That's why the current is moving very fast. This is given in one of the lectures given by, if you interested in these type of lectures, so just you go for Digvijay, sir, ISC Bangalore. Very good lectures are there. Okay, you just, I will suggest this one for the basic for the VLSI devices if you want to like make command on that one. Okay, and for the circuits, IIT Roorkee Sudev Das Gupta sir lectures are very good. Although you are already, I think you are already did more NPTEL courses and all, so they are giving the courses also there. Okay, so this is the thing. Now when we are connecting from this, so this is the punch through, means this is type of a breakdown, right? So the current is flowing from here to there. So this is the type of a breakdown we are saying. This is the punch through breakdown. So this is the advanced conditions, mean that last condition for the DI bill. Okay, so this is the formula for the DI bill, what we are using in the research. Very simple formula. VT at low BDS, VT at VDD, and V supply and VDA. Means like suppose this is the 5, means we have taken that VT at 2 voltage, then at 5 voltage, then whatever the supply voltage and whatever the VD low we have taken. So we are just using this to find the DI bill. So VTH we have already discussed. Sorry. So now there is another thing, surface scattering. This is very important phenomenon because it is related with the VLSI technology as well as the VLSI devices. Because most of the things are I'm working on the devices, so my like the things are coming from the semiconductors and all those things. Okay, there is a lot of ways to explain one thing, right? You already know, you're all our teachers. So surface scattering. So the velocity of the charge carrier is defined by the mobility of that carrier. Mobility means like mobile. We are using the mobile. Why we are calling it as a mobile? Because it is we can able to take anywhere, right? This is very mobile. Take very easy to take, right? Very small. So mobility is more. Same thing. Mobility means freeness of the charge carriers to move, right? And if the freeness of the charge carrier, definitely the velocity is going to be increased. So the velocity of the charge carrier is defined by the mobility of that carrier times the electric field along the channel. So it depends on the electric field also. Okay, what is electric field? This is because you all are teachers, you already know us. But yeah, I'm explaining the students in this way, like electric field. What is electric field? Electric field, generally when I'm telling electric field means like the field, some field. Like I'm giving the example of the football field. Like there is a football. So when the two teams are playing the football, everyone is concentrated towards the football. Like same thing happened in the electric field. Electron has some like repulsion or attraction to someone. Like some electrons are going to be attract and holes are going to be like whatever the charges. Same charges are going to repel. So the field up to which, right, it shows some effect. That is the field. Simple thing, right? This is, and we know how we are calculating the electric fields and all those things. So it's not like, because this is to explain the students, we need nowadays, we need some analogy to just compare with some physical environment, physical thing. So students recall the things immediately. So this is good actually, habit, analogy or storytelling methods, many methods are there. So like the same thing. So when the carrier travel along the channel, they are attracted towards, actually when the carrier is, there is always electron follow the zigzag path. It is not going like straight path. It is just losing energy, then another getting energy, losing energy, recombination, generation is going on every time, right? So when the carrier travel along, they are attracted toward the surface by the electric field created by the gate voltage. As a result, they keep crashing and bouncing against the surface during their travel following a zigzagging path. This effectively reduces the surface mobility of the carrier. Definitely, because every time you are getting an accident with the wall, like how you are maintaining the speed, it's very difficult, right? So as a result, they keep crashing and bouncing against the surface during their travel following a zigzagging path. This effectively reduces the surface mobility of the carriers in comparison with their bulk mobility. Now, these are two mobilities are there. Surface means this is the, and bulk means this is. Bulk means inside, like If we are talking about the ocean, so ocean, when we are going deeper inside the ocean, then we are saying this is the bulk. Everywhere there is a water. But when we are working on the surface, so and you have seen also all the fishes, most of the like things are traveling, or we can say swimming on the surface, not inside. Right? There's something is there. Right? Everybody needs oxygen, whatever the things, but on the surface, right? Because the speed is more there. So this effectively reduces surface mobility of the carriers in comparison with their bulk mobility. So the change in carrier mobility impacts the current voltage relationship of the transistor. So if you see, this is the simple diagram. So as the electron travels through the channel, it is attracted the SiO2 interface and bounces against it. This effect reduces its mobility. So due to short channel effect, electric field increases and mobility becomes field dependent, right? Surface scattering occurs, average surface mobility decreases, right? So, and there is a hot carrier electron, like hot carrier, HCE, hot carrier electron. There is one question during my PhD time. One of the examiner asked, why we are calling it as hot carrier. Hot carrier is very hot. No, sir, it's not hot. Actually, it is highly energized. That's why what happens when suppose anyhow one charge carriers from here or there anywhere, it comes and it contains some neutral item. It bombarded with that one. What happens? The one electron and one hole here, because it contains something but whole electron pair, but it splits into two. Now what happens? Electron electron went to the substrate. Electron go to the substrate, and this helps in current. So anything can be happen. Due to this, there is a problem, latch up problem. So due to latch up, the whole chip is going to be zero. Means yields is decreased like anything due to latch up problem. So we will discuss if the time permits. So hard carrier electron is effect is also very important to remove, right? And this process of getting like splitting, like bombardment of the charge carrier with the neutral atom, okay, this is known as impact ionization, splitting into two. So the hot carrier exhalated by the high electric field can have a different fate as well. The energy it contains may be sufficient to enter the oxide and get trapped in it. The trapped electrons after transistor response to the gate in the form of increased threshold voltage permanently changes MOSFET switching characteristics. So many things can be possible. So how they manage to enter the oxide and get trapped? This is also possibility. Trap into oxide. If trap into oxide, then again the threshold voltage is going to be affected. So it is like like just we are doing some it's very near to the real when we are talking about the roads and all those things. So to reduce the formation of hot carriers and their negative effects, what we are to do, we are making one NMOS. Now step response will come. Here is high because what we have step means the electric field reduces like this, linear, or we can say it's not abrupt immediately. It's somehow linear type of. So that like we can manage the changes like this. We are thinking in this way. So lightly doped LDD are going to be grown near the N plus regions to like reduce the strength of lateral electric fields and therefore reduce the formation of the hot carriers. Okay, so this we have already. Now there are some concepts are there, subthreshold swing. As I have already known you, biasing NMOS in like this is the value. What I am telling you that last time, this value is always 60 millivolt per decade. It is not possible to get in the case of this because actually when we are talking about MOSFET, because now the things are coming, when we are talking about MOSFET, in MOSFET, the charge carrier has to cross this barrier to reach another, right? But when we are talking about the tunnel FET, in the tunnel FET, the mechanism is different. This is known as thermionic emissions. But in the tunnel FET, we are transferring the charge carriers from one band to another band. This is band to band tunneling, means the conduction of band of one to the valence band of one, like this. So like this, we are transferring the charge carriers. Okay, so it depends on the density of states, it depends on the Fermi-Dirac statistics, many things are there. And basically, this is the quantum phenomenon. For this, we need to learn about the, if you are going for the analytical modeling, you have to go for the Schrodinger equations, quantum, like quantum mathematics and all those things. Quantum physics, we can say. So controlling effects of scaling, we observed in the previous section, if the channel length is small compared to depletion region, short channel effects becomes intolerable. This limits the further reduction achievement in gate length. To limit these effects, the depletion region width should be reduced with corresponding reduction channel length. Means reducing of the depletion region. Depletion region width means this we have to, because here this white one is there. So we have to reduce this depletion region width. Here also, that's why we have make one N plus region. Because of that one, the depletion region depth is going to be reduced. Because if we reduce the depletion region, so because what depletion region? Depletion region basically contains the immobile charge carriers, if I'm not wrong. Right? Immobile means like which are not ready to move. Like suppose one electron is moving always for the hole. Hole is moving for the electron. We believe in this. Okay, when electron combines with the hole, what it will do? It will not move. Then what? It is just like a traffic jam. It will not allow any other charge carrier also going to be moved, because now it's a traffic jam. Okay, but depletion region, electric field is also only generated in the depletion region. This is also important. So there is a like many things are there. Okay, so this can be achieved by either increasing channel doping concentration, because if we increase the doping, what happens? If we increase the doping, definitely the depletion region thickness is going to be decreased, because already N plus is there. Here also we increase. This is also, but or increasing gate capacitance. Gate capacitance means area we can increase, and many other methods are there. Or both. Gate capacitance determines the gate control over the channel. So controlling effects of scaling, increasing channel doping concentration, increasing gate capacitance of both, mobility booster, gate leakage reduction, and polydepletion elimination. Many methods are there. So there is some technologies are coming now. This is the strained silicon technology. It's already employed by the Intel in 2007, I think. Okay, Intel's baby. Then many others, like there are two type of strains we can able to induce. One is biaxial strain, and another one is the uniaxial. We are not going to discuss about these things because our topic is tunnel FET. We haven't started yet. So I'm coming to tunnel FET now. So now to reduce the short channel effects, we need some different geometries. We need some different mechanism. So first we are working with the different geometry. So this is the different geometry of the like MOSFET, like different geometry as well. Now if you see, this is the double gate, right? This is the nanowire FET. This is the multi-gate FET. This is the FDSOI. This is the NAMS. This is the carbon. This is the nanosheet nowadays coming. This is the CNT FET. This is the multi-channel FET. This is the FinFET. FinFET, if you see, this is controlling by 3. So now FinFET is more before around 5 years. Now gate all around FET we are using. So fully depleted, what is fully depleted? Fully depleted, just I'm coming to the part because, time is less. So fully depleted, this is the fully depleted. What we have in the conventional MOSFET, we have introduced one buried oxide. Now what happens? Short channel effects, hot carrier electron is going to be stopped here. Why? Because now there is an insulator. How the charge carriers will penetrate the insulator. So this current is stopped, this current is stopped, everything is stopped. Depletion region is also limited. Why? Because how you can make the depletion region in the oxide. So using oxide, many advantages are there. Negligible drain to substrate capacitance. This is also because now two capacitances are formed. Here is suppose here is one capacitance, another capacitance here. So now if you connect the capacitance in series, it's going to be less. Small body effects, fast X, because of the leakage is reduced. Body effects are also reduced. No latch up. How latch up will come? Latch up is basically SCR is formation. Okay, might be your teacher, you already know. So we are stopping the latch up because how the another means like conduction path is going to be, because this is the insulator is insulator. You can't able to the charge carriers will not penetrate this insulator. This is the so simple device isolation, smaller area, accident radiation hardness, small junction leakage can reduce short channel effect. This is the advantage of the ATAL. Now we are coming to a structural engineering. Okay, what is structural engineering means? First we have, like suppose there is a one simple example, like suppose there is a one student in your class, you all are faculty. Okay, so first year student is there, because we know in the first year the student is very enthusiastic to do the work. He wants to learn everything, right? First year student. So now what happened? First year student is there. He came with very enthusiasm and he is working day and night and he's trying his grades and all those things. Up to second year, he is affected by the environment. Now the things are loose. He's not so much good, but his father is very passionate about him. So father said, you have not to lose your efficiency. So father, what he did, he just asked the teacher, okay, you also control, I will control at home, you will control at the college. Now this is the double gate type of thing. Efficiency is increased because the controlling is from two ways, from the upper part as well as from the lower part. After that, what happened? Still, because student affected by the environment, second year, because we know first year when the students will come, is full of enthusiasm. He has an ability, just his thing is I'm going to be an engineer and I have to be best. I'm getting this much of a package. You know, the first year students. Right. Then second year, little hope is less and affected by the environment. Then third year, more. Okay, I have to leave. Just I have to go from this degree. Anyhow, I have to find some job like this. But because the efficiency is decreased due to the environment and also the everything, he has to spend the time. So that time, the controlling. Then his father said, okay, now it's also we have to continue the efficiency. So what he will do, he will ask one of his friend, student friend, you have also control. I am controlling from here. Sir is controlling from, teacher is controlling from here. Now you have also have to control. Now three ways controlling is there. Definitely the efficiency is there. So in 2014, around 19, we are using this technology, FinFET, controlling from three ways. Okay, from here, but the fabrication of this is also a little bit challenging because, but okay, it's okay. Nowadays, what happens? Gate all around we are using. We are controlling from all the way. Now, after that efficiency, still there is a problem. So in the fourth year, to make the same efficiency, what father did, he has given one particular guard, bodyguard, whatever. He has to be always with you. Whatever you are doing, he has to watch. So your efficiency is 100%. Now this is the gate all around. Means gate is wrapped over the channel. So the controlling is very high. So nowadays, if we are seeing gate all around, we are using. Now FinFET already I have discussed. Now our topic is, this is magic. This is very important slide. Taiwan, I have taken from the Taiwan TSMC website. So if you see, this is 1989, what we have started. And if you are coming to 2028, now we are using A16, then A14, then 2 nanometer. 2 nanometer means this is also known as N2 technology. Something is there. We are not going to discuss everything, but just I will give you some overview. Nowadays, in 2028, this is predicting 1.4 will come. 1.6, already 2026 is the prediction. 1.6 Armstrong. 1.6 nanometer means like 112 Armstrong, if I'm not wrong. 12 Armstrong. Armstrong means this is the unit of the electron, 10 to the power minus 10. So now this is the Armstrong units we are. Armstrong scale we have already entered. Okay, now 3 nanometer we are using. iPhone, what you are using, it contains 19 billion of transistors and it contains A18 processor which contains 3 nanometer of a transistor. And this is gate all around technology. Now 5 nanometer technology, if you see, this is the like 3 nanometer is in 2022. Still we are using 3 nanometer in the research, means in the market. But 2 nanometers already 2025 is already made. Then A16, A14, the things are coming. So now if we see Taiwan Semi, this is taken from the Taiwan Semiconductor Manufacturing like website. So A16, 1.6 nanometer Armstrong class, 1.4 nanometer Armstrong class. Then this is 2 nanometer class. Transistor architecture, all use gate all around field effect transistor, what we have just seen. So nanosheet transistors. A16 introduces super power rail. There is some type of a thing we will, because the time is less, might be we will in future, some other lectures, we will discuss all those things. So A14 evolves NanoFlex Pro standard cells for better layout flexibility. Then N2 debuts gate all around fed with optional backside power delivery BSPDN. So there are some algorithms are there. We are trying to increase the power. We are stopping the power dissipations. We are trying to increase the current. These all things are regularly we are doing. So performance, 8 to 10% speed, 15 to 20% power versus N2P. Then A14, 15% speed, 30% power versus N2. N2, 10 to 15% speed, 25 to 30% with N3, means 3 nanometer. Then logic density up to 1.10 versus N2P. Up to 20% increase versus N2, 10 to 20% versus N3E. Design innovations, SPR enables, SPR is super power rail, right? Enables tighter routing, lower IR drop, preserved gate density. A14 NanoFlex Pro boosts performance per watt and design flexibility. N2 advanced EUV lithography and DTSCO optimization. Target applications, AI, A16 processor basically, 1.6 nanometer. HPCs, chiplets, dense computer tiles. A14 smartphones, smart glasses, Edge Eye. N2 mobile SoCs, AI accelerators, automotive, NHPs. HPC. Productive timeline, risk in 2026, volume in 2027. Volume expected 2027-28. Volume production begins in 2025. N2. Till now we are using 3 nanometer. So now we are coming to our topic, tunnel. Actually, this framework is important. Tunnel field effect transistor is just like different mechanism. Like it depends on the tunnel diode. what we have studied before. So this is the simple what we have to change in the conventional MOSFET. In the conventional MOSFET, what we are using N plus here and N plus here. But in the tunnel FET, what we are using N plus here and P plus here. Means we are using the opposite type of a doping. Why? Because we need this type of a structure, sir. Right. There is also current known as ambipolar current. Here one is on current, one is ambipolar. Means if we see the graph of that one, we are getting something like this. This is on current and this is ambipolar current, we are saying. Because it's like pin or nip structures. Means P-type, intrinsic and N-type. And this is also, and the major thing is doping should be very high. That's why we are getting more, we are getting like we can say the degenerate type of a semiconductor here. Degenerate, what we are degenerate means that Fermi level should be inside the semiconductor, above the line of conduction band, top of conduction band. This is degenerate type of a semiconductor. So tunnel diode is just working on that one. Nanovars. So this is like something is there. So this is nanovars, and this is my research work is basically I'm working on the nanotubes. So this is also means here we have gate all around. Here we have controlling from inside as well as from outside. So there is a too much big good controlling, and I have around 10 or 15 SCIs generals on this only structure, because this is not dead by. This is if you just search my name, you will get my papers here. So generally I'm working on the nanotube FETs. Okay, nanotube, and then tunnel FET also we are using, means nanowire tunnel FET, nanotube tunnel FET, fin FET tunnel FET, like fin tunnel FET, then junctionless tunnel FET, then because tunnel FET is different mechanism. We will go for the tunnel FET now. So if you TFET is basically a pin diode and 3-4 terminals, like same thing. Okay, it uses the applied voltage to control flow of. If you see here, we are just the things are coming like up, but here the things are coming band to band tunneling. So this is the major difference between that one. And for this, what we need some empty density of states here. And we are getting it easily. It's not a big issue. Okay. And then we need the depletion region should be very less. Means there should not, doping should be very high. So that's why doping should be high. This should be very narrower. So quantum tunneling has to be happen, and then the direct charge carriers. And the major advantage in this, low power. Why low power? We are saying always tunnel FET is low power because no need to excite the charge carrier thermionic emissions. You have to excite it using temperature, using electric, it has to jump. No, just we are transferring it from here to there. That's why it's low power. Okay, so this type of a device whose main principle is based on the band-to-band tunneling mechanism of electrons. MOSFET carrying the mechanism is based on thermal injections over the barrier, right? So this is the tunnel FET, and this is the normal conventional FET. So this is the major structural difference. Only you have to make P plus like this. So tunnel FET is generally the things are electron tunneling from valence band to conduction band of this. This is the off condition. This is the on condition. When we are applying the voltage, what happens? The barrier is going to be down, right, for the conduction band. And this is the valence band. This is also down, but here is not going to be, because here is only the change are going to be happen. No? So the things are coming like this. So tunnel FETs operate by exploiting quantum tunneling effects to control the flow of electrons through a semiconductor channel. So band to band tunneling. So what is quantum? It is when a particle can pass through a potential energy barrier. Okay. So tunnel FET versus MOSFET. So low leakage current due to a reverse bias tunnel junctions, high leakage current due to thermionic emissions, sub 60 millivolt per decade. As I have already told, there is one formula. We have seen KT by Q, then 1 plus CD by CG. Something we have seen. So this is when, because of this KT, what is KT by Q? This is VT, thermal voltage, right? So it is constant. We can't able to get below 60 millivolt per decade. But when we are talking about the tunnel FET, it is easily to go. This is the major advantage for the tunnel FET. So we are getting the good subthreshold slope, good switching speed at the cost of low power. So that's why there is a different mechanism. There is no structural difference. There is a mechanism difference is there, right? So downscaling does not, it's great because when we have to work on low power, we can integrate more number of transistors there. So this is the major advantage. So downscaling decrease in, if we are talking about the MOSFET and the tunnel FET. So in the MOSFET, downscaling degrades device performance, but in the tunnel FET, downscaling does not degrade any type of a device performance. So reverse bias pin body causes low on current. Here thermal current high on current. Gate, there is a disadvantage of the tunnel FET. The on current is going to be very low. This is the major disadvantage in the tunnel fat. So gate drain capacitance is dominant. Gate drain capacitance equal to gate source capacitance. We will discuss, might be time permits. But tunnel fats have also some issues, definitely, because we have to research again. The research is not going to be ant, right? So tunnel fat basically low on state current, what I have told, and the ambipolar condition. Low on state current mean the on current is very less because the voltage force is less. Voltage is less, right? Speed is less. So definitely the current is, because when the things are coming from the slope, like if the things are coming from the mountain, right? If the vehicle is coming from the mountain, its speed is high. But to reach the mountain, also you need the more speed, more current, right? More force. Force is just like a voltage. Speed is just like a current, right? So, and the another one is the ambipolar. Ambipolar, when we are talking, so this is the ambipolar. This is also because it is also working in the negative direction, which is unwanted for us. We don't want that one. So this is also we have to control. So produce high electric field at source channel junction. This we can. This is the solution. Produce low electric field at drain channel junction. This we want. So now these are the some of the methods what I have already employed in my papers, and I have published many papers on this. So dielectric engineering, dielectric pocket we have already placed. Heavy source doping we have already doing it. Means source generally we are putting 1E20 and drain we are putting 5E18. This is, and then reduce oxide and body thickness we are doing it, because when we are actually we are using EOT nowadays. We are using HFO2 and HFO2, and generally in the simulations I am using 1 nanometer. But when I am comparing with the silicon effective oxide thickness, it becomes 6.2. So because if we increase the effective oxide thickness, the tunneling is reduced. Okay, and the current is more. So there are some methods are there when we are doing the simulations and all those things. Now these are different type of tunnel fats are there. What I work, this is the structural based differences. Actually, this is not my work. One of my student in Ethiopia, Jorosen Getachew. We have already published one paper on this on micro and nanostructures last year. So this different type of structures we have utilized, and we have utilized the silicon germanium pocket here, because we have utilized this one because, as I have already told you, that the tunnel fed has low current. So we have to employ some method by which we can able to increase the current. So we have using this thing, because if I am putting SIGE, many properties are there. Although SIGE is also one of the strain type of material. We will discuss some other time what is strained silicon. This is also good for uniaxial, biaxial strain. Many things are there we can discuss. Okay. So generally what happens when we are using this type of a material here in anything between the channel and the source, right? If we are using here, so it will reduce here, but we are using this type. So here we are enhance the on current. Here we are working on the off current. Here we are working on the on current, means ambipolar current here, right? So this is the thing. So same thing, this is the so this is one of the one structure SIG but DG double gate effect, right? So here we have used the stacked gate TiO2 SiO2. Here we are also using stack, but here we are using HFO2. Okay, we are not getting the good readings here. That's why we have utilized it, because the comparability we don't know. Sometimes the simulations is also, we are something is here. So we have utilized here TiO2 is higher dielectric constant compared to the HFO2. So this is one we have used. This is another. Now this is the jet shape. If you see, this is like a jet. That's why jet. This is the double gate. So here if we see, this is the vertical defect, because we have taken the gate here and the source and drain here. This is source. If you see, this is source, this is drain, right? And the another one, then last we have used the U shape. This is the best structure what we have, right? We have also worked, one of my students, she worked on Charlotte, he wanted a broken gate defect. I haven't included anything in the slide. Now one of my students, she's also working on the tunnel FET, but she worked on the heterostructure based tunnel FETs. Like we have utilized the indium phosphide, and then we are working on the photo detectors. By using this, we have working on the gas sensor. And by broken gate defect, we have worked on the biosensors. So FET based biosensors also we are now, because we need some applications when we are going, because everybody is looking for the publications nowadays. All universities are also forcing to, we know, right? So what we are doing, we are working on different type of things, sensors, because now we are doing research, and if the fabrication laboratory will come in India, so definitely we have to go more number of sensors we can able to fabricate and we can distribute, because the costing is getting very low. It's less than 1 rupees. right? And the size is also we know, right? So this is the U shape, and all are using. We have used the non-local band-to-band tunneling. There is a local band-to-band tunneling, non-local band-to-band tunneling. So we have utilized the non-local band-to-band tunneling, and this is the like we have used the source concentration, channel concentration, drain concentration, channel thickness, drain and source, channel, everything we have. Okay, so this is the conventional DG-FET, means double gate TFET, and SIGE pocket. So how we are enhancing our current? See the red one and the blue one. There's a too much difference, right? And when we are working with the different type of dielectrics, so Al2O3, aluminum oxide, aluminum dioxide, then HFO2, then TiO2. So you see, when we are using the higher dielectric, so we are getting more current, and but the slope is little bit, but okay, okay. And when we are using different of even in the jet shape, if you see jet shape conventional is this one. When we have introduced the SIGE pocket, the on current is going to be increased. So same thing, conventional VT-FET, and the doping also, source doping concern in the vertical TFET. If we are increasing the doping of the source, also we are getting more current. So we have tried to analyze all the aspects, how we can able to increase the current on current. So we tried for all the aspects and we got some good results in that one. So here is also you see U shape and SIGE U shape. This is also the electric field of that one. And if we compare all, so if you see the U shape is we are getting very good. I have taken the same color by mistaken. Okay, I will take this one. You see. Okay. Although there is something we also working on that one, why we are getting like these type of things. But if you see the U shape is maximum, then vertical is good. Okay. Then jet shape is good, then DGT fit is there. Right. So we have seen some differences are there. So why we are getting U shape? Because of the geometry, basically shape. So this is the structural, we can say some structural analysis of the structure we did. Okay. Okay. And although if we see the subthreshold swing is maximum in this one in the vertical defect because of its orientation, channel and line quantum tunneling. There is a two type of tunnelings are there, point and line, right? So this is the international technology roadmap for semiconductors, ITRS. We are following this one. Still, tunnel FET is in the research. It's not like completely dead. Now there is a junctionless FET. What is junctionless FET? It is just like a FET, but here we have not using any type of junctions, right? We are not using any type of junctions. Means we are controlling the things over the things. Like here is one, here is one. This is the conventional. We are using N plus N plus. But here we are using only N plus bar. Finish. Here we are using source. Here, and how we are making the source and drain? By using work function engineering. By using work function engineering. Now, what is work function? Means we are putting different type of metals. Okay, and then we are making the P type and N type there. Here. Then we are making here P type, here N type. Like this. We are not using, and if the junctions are not there, suppose if there is no barriers on the road, then the mobility is good. Means the speed is good, the current is good. So same concept we are utilizing here. But here we are utilizing some work function engineering to make the peak, because we need some difference. If the difference is not there, then how the charge carriers will move? Like two buckets, if you have, and if you are filling with the same level of water, how the charge carriers will flow? It's not possible, right? So we have to see in some practical aspect of that one. So all the existing generally have junctions. If you're talking about BJT, MOSFETs and all, right? MESFET also, JFET also. Like we have seen this. Disadvantage of the junctions: decreases mobility, heat dissipations, difficult and expensive to fabricate. Because definitely if you have to put N plus, then P, you have to put more number of money there, right? Source of current leakage. So miniaturization has reached limit. Junctionless transistors can help chip makers to further reduce the size. Although junctionless still now nobody has made, due to some might be fabrications facilities we have to revise, right? This is also a big money like thing. So the junctionless transistor is a multi-gate FET with no PN nor N plus N, nothing is there. Like we are using only N plus, like the support structures. So the device is basically a register in which the mobile carrier density can be modulated by the gate. And when we are talking about the tunnel FET, like here we are putting the gate something, and we are controlling the flow of charge carrier using this gate only. We are applying the electric field, then we are beginning. But when we have to make the tunnel FET, so we are applying different type of work functions here, and then they are controlling the things. So generally, this is the junctionless FET, right? Generally, we have change some like to make it good, some doping level we have differentiate. So this is the junctionless FET, LT junctionless TFETs, right? Tunnel FETs we are using. So here different work function, here different work function. When we are talking about the tunnel FETs, so this is junctionless tunnel FET. This is the junctionless FETs. So they operate by controlling the flow of current through a semiconductor using a work function and quantum tunneling effects. No junction, no doping gradients, high doping concentration. So it is energy required to remove an electron from the surface of Fermi level and move it to work function. What is the work function is saying? So properties of GLT: drain current increasing with doping and channel thickness, leakage current increases with channel thickness, dielectric constant, gate controls improve with dielectric constants, short channel drastically because nothing, no junction. So how the short channel effects will come into existence? So threshold voltage variability also we are getting. So many things are there. Like this is not our topic although. So this is the basically junction transistor and junctionless we have already discussed. Now there is a one heterojunction TFET also, because there are a variety of TFETs are there, and there are a lot of things I am working on TFETs and around I have 25 SCI generals on TFET only, basically on TFET, right? So I'm working on TFETs only. So this is only the SCI and scope of generals. Conferences are different. So many ideas, many researchers are working, many students are working. So we have many type of trying to because I am also from like one of the private university. I know the things. We have no more facilities also. So how we are going to publish the papers? All those things we have already. This is the big challenge for us because the things. But yes, anyhow, we are trying to do something like So heterojunction defects like material engineering, we have different type of a material. Hetero means different type of a material we use like INAS, GASB, SIGE to create a heterojunction for enhanced tunneling. Then band discontinuity. This is actually due to this band discontinuity is coming. The time is not there means when we are making the band, so we are getting like this and some here. So here we are getting some like this something. So here sometimes we are also getting 2DG type of things. This is like two-dimensional electron gas, and this is generally coming when we are using the undoped algan and GAN type of materials. So this is also already it's 2010. It's already started. There's a big research on the GAN type of devices also. GAN is also all the floodlights what you are using. This is type of a gallium nitride of like you have seen stadiums, light bulbs. All these all are gallium nitride now. There is a gallium nitrides. Then there are There is antimonides. Then nitrides. Then there is a second, fourth semiconductor, second, sixth semiconductor, then third, fifth semiconductors. A lot of compound semiconductors also have a big research scope actually. So interface complexity requires precise control of lattice matching and interface quality. Then higher on current potential due to favorable band alignment and tunneling. There is now one more thing, graded band means we can control the band gap actually, graded band gap. This is also possible in the Silvaco ticket itself. I'm working all my things in the Silvaco ticket from last 10 years around. So now this is the FET-based biosensor. So I think the time is not there. Already we have reached our threshold because I think the another lecture is there. So might be in future sometimes we will discuss about these biosensors and gas sensors. I think so. Sir, are you listening me? Shall I continue or I think it's hello?
Avadar Singh sir.
Yes, sir.
First of all, let me thank you for giving an excellent session to start with for this FDP. I hope the participants have got enriched. And dear participants, if you have any questions, please ask.
Sir, good evening, sir.
Good evening, sir. Yeah.
Sir, I am doing my research on now. I am started research on gas sensors, sir. Could you please give me some suggestions? Which structure is familiar for gas sensors? Vertical structure or simple SOI structure or double gate structure, sir?
See, nowadays, if you want to do some research on the gas sensors, because this is now already saturated field, what I'm suggest you come to the photo sensor. Photo sensors is good, but if you want to do the on the gas sensors, then do some comparison type of a thing. Like prepare, like go for some material, whatever the material you are using. I don't know which germanium or silicon, whatever. Just make some structures and compare some more gases like oxygen, ammonia, some 2 and 3 means there, if you want to, because I know if you are started your research, definitely you are doing for PhD, if I'm not wrong, right?
Yes, 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 sir. I have found more hydrogen gas sensors.
Hydrogen,
Maximum I have found hydrogen gas
yeah,
sensors. Yes.
palladium, hydrogen, you are getting the combination of that one, I know. So what you can do, there
Yes,
are
yes, sir.
many type of metals, like what you, if you have already started, you know, we have to vary the work function only. Okay. And then because
Yes.
we have no any material, we are using palladium work function, I think 4.25 or something like this. Okay. So we have to vary that one, and we are putting more intense of gas, then the work function is going to be changed, right? So what you do, what I suggest you do one with the hydrogen with one metal, palladium, then go for another with another metal, then 3 and 4 metal you compare. So that is the good work, and believe me, the paper is in one time is going to be accepted. And also there is one thing, when you are submitting a paper, you have to see, because there is a time of the journal, what we are believing. Now, if you are putting the paper on the macro and nano structures, there is a good chance to accept, because there is a something they are working on. I don't know, but from my last 10 years career, I'm seeing sometimes it is super lattice is very good. Super lattice and some structure is there, right? Then silicon is very good. Then macro and nano structure. Sometimes microelectronics reliability. There's something is there, you know. So you just see which general, because it depends on the time and all those things also. Any other things, sir? Might be I answer your questions. I don't know. Yes. Sir.
Okay, sir. Okay, sir. Thank you, sir.
If anything, you can contact with me anytime. No problem, sir. I'm always here.
Okay, sir. Thank you very
Sir,
much.
good evening, sir.
Good evening, madam.
Sir, is there any best techniques are used in the gate all-around to reduce the low power, sir? What are the
Sorry,
best
ma'am,
techniques?
Could you please repeat?
What? Okay, sir. What are the techniques are used in the gate all-around FET to reduce the power, sir? What are the best techniques?
Basic techniques. Which material you are using, ma'am? Means tunnel FET you are asking, MOSFET you are asking, junctionless FET you are asking, negative capacitance FET. All are different, right?
GAFET, sir. Gate all-around FET.
Any gate all around, ma'am, see, if you are working only on gate all around FET, nowadays it is what I believe it's already, so because it's already now in the market, gate all around FET, now all the transistor, all the processors are making on gate all around FET. Now if you want to publish a good work, so work with the TFET, gate all around tunnel FET, or if possible include gate all around junctionless tunnel FET or dopingless
Is
tunnel
it
FET.
possible, sir, to do the junctionless FET, sir? Is it available? Is it available now?
Ma'am, in the research, it's more paper are coming. It's no issues. Research is, because I already told, major problem is they have to devise their fabrication laboratory.
Hello.
Yeah, might be some complexities are there. I don't know, but in the research, the junctionless FET is everywhere. You just search and gate or all around junctionless tunnel. If you are making, then it is. I think it has a good potential for some research paper. Yes, ma'am.
Okay, sir. Thank you, sir.
Most welcome. Yeah, any other question, sir, madam?
Any questions
evening,
from
sir.
Participants, please?
Good evening, sir.
Sir, I have very basic question in circuits. We all know the working of transmission gate.
Yes, sir.
So in transmission gate, if we remove the VDD and ground from the substrate terminal of PMOS and NMOS respectively, and instead of that we connect the substrate to directly to the source, I just wanted to know what will be the effect of this change in the circuit.
Sir, actually, because we are using in what I know is in transmission gate, we are using one PMOS and one NMOS, right, sir?
Yeah. Yes.
Yeah.
Sir.
So when we are connecting the source of the PMOS to the ground, how it works? Just think.
No, source of the
because generally we are connecting the source of the PMOS to the VDD and source of the NMOS to the ground. If I'm not wrong.
Yeah.
Yeah.
Yes,
So
sir.
how it works? It's not possible, sir. That's because it's against the basic concepts. Means we have to think, might be because we are connecting source with the with the ground. So VDD means because it's like, when we are using the things, it's just like a capacitance. First, think about the capacitance effect. The MOS, first thing is dielectric is there and two plates are there. I suggest you one book, sir, because I am working on the devices. So my mind is coming on devices directly. So I suggest you one book, sir, if you want to explore. Cividis, TSIVIDIS. This is very good book for the MOS modeling. And it has given the chapter like double gate, means two terminal MOS capacitance, then three terminal MOSFET, then four terminal, like this chapter it has given. And this is a very good book. Even the lectures are also there. Cividis, TSIVIDIS.
Sure, sir. Thank you, sir.
Okay, most welcome, sir. Most
Sir, good evening, sir. It's my general question.
Yes, sir.
Is the quantum computing changes any Moore's law, sir, in the future?
Sorry, sir.
Quantum computing is there, sir, right now. Because of that quantum computing, is there any changes of the Moore's law?
Actually, I haven't, sir, worked on quantum computing till now. Even I heard only like some, because quantum, when we are working, these are tunneling type of things are coming, Schrodinger equations or all those things. But I haven't much familiar with that one, sir. Sorry, sir.
Okay.
No problem.
Thank you. Thank you.
Most welcome, sir. Any other questions, sir?
Avtar Singh ji.
Yes, sir. Sir.
One of the 2-3 participants have posted their questions in the chat box. I request those participants, please just unmute your mic and ask the question to sir directly.
I am unable to see the chat box, sir. I don't know what.
That's why, sir. That's why I'm asking the participants themselves to unmute their mic and ask questions. Or else even I can read out.
Or you can read out, no problem, sir. Yeah.
Murli, sir, please see the questions posted in chat box and ask one by one, that sir will explain.
Okay, sir. Sir, the question is, sir, in academics, we are having conventional CMOS devices and circuits.
Sorry, sir. Please repeat. Yeah, please repeat.
In academics, we are having conventional. In academics.
Yeah, in academics, okay.
We are having conventional CMOS devices and circuits.
Yeah.
Does the advanced MOS devices circuits are same as conventional circuit? That is the question, sir.
Yeah, sir. In academics, we have limited up to MOS only. But nowadays, we are not using MOS anywhere. Like we are using, as I have already told, then in Apple A18, means Apple iPhone 16, we are using more than 19 billion of transistors, and it is gate all around TFET. We are not studying. If you are going for the MTech, might be from the good colleges like in IITs or some of the NITs and Thapar and like the VIT, SRM. Now they have included these things like gate all around, like structural type of a thing. And when we are working, because the major thing is, might be the person will understand, we are working whatever in academics we have, we are still not considering the short channel effects. We are working with only the square law model. If you see the Kang book, because this is the basic book what I am also teaching my students using Kang. So there is a second chapter. If you see, fourth chapter, sorry. This is the models, like MOS models. So first model is square law model, then analytical model. Then we are coming to BSIM4, then we are coming with the short channel effects going to be considered in BSIM4 model. Okay, so it depends like what type of study you are doing. If you are going for the PhD, definitely you have to study everything, else it's not possible. I think I explained it, because we are working on more on the assumptions. We are working on the square law model, means like a parabola type of a figure. But when we are going with the analytical, more process parameters are coming into existence. Okay, so there is an effects of that one, because it's like a science. We are putting more mind, we are doing more modeling, and then we are getting more things, because most of the things are working on the assumptions when we are working with the academics to make it simpler, too easy for the students. Right.
Okay, sir. Okay.
Yeah. Next, sir.
Second question also asked by the participant only, sir. No problem. These two are questions arising in the chat box.
Okay, the same question.
Thank you. Yes, sir. Thank you, sir.
Yeah.
Thank you.
Okay. Anything else, sir?
Sir, one more question. Just now, Ahmad Shah participant posted. In which tool you have simulated circuits based on TFET? And if done so, which model file you have used? This is the question, sir.
Yes. Actually, thank you for this. Is actually the questions which I am expected from the participants because they are
Hmm.
PhD students. This is they need it. So, sir, simple thing. I am using the Silvaco ticket tool and circuit. I have prepared because my major work is on the device. So I'm working only one MOSFET, basically means one transistor, and I do the analysis as the analog performances, RF performance, and in some of the paper, what I did, I prepared the small circuits like current mirror, VCO, then simple NAND gate, AND gate, inverter like this, because up to 25 components you can able to use what device you prepared. Even you can use two devices also, like one PMOS and one NMOS also you can utilize. Okay. And after that, if you want to do further analysis, then there is a one tool of the Silvaco ticket. It is known as Atmost. So you do the compact modeling, you are getting the parameter extraction from that one, and then you are putting that parameter, and you can do some like modeling in Verilog also, and you can extract the parameter, you are getting the values, then you can prepare the compact model. Like you have already know, we are using Eber's small model. We are using many models like this, hybrid Z parameter, Y parameter. We have studied in before transistor small signal models, right? So we are preparing that type of models, and then we are going to utilize in some tool like Cadence and all. But I haven't worked on that one. I only heard. My work is particularly on the devices, and I'm using like biosensor, like simple current mirror, simple amplifier, up to 25 components.
Okay, sir. Okay. Thank you.
So anything else, sir?
Any other questions from participants, please?
No, sir. Yes, sir. No.
Sir, since your PhD research area is this, can you give any suggestion to the faculty who are joined in this FDP? They are at junior level, sir, as I have seen the list, maybe 3 to 5 years of experience in teaching. Please provide some suggestions to how to start their PhD in this vibrant area.
Major thing is, sir, what I am suggesting, see, if you are working in VLSI devices also, come with some like see the environment, like what is the requirement for the market. Because see, if we are seeing for the academics job nowadays, it's very difficult. It's very difficult because of, you know, all the things are already available on the YouTube's, many lectures are there, NPTEL and all those things are all there, and they are much better. So better you will learn some skill, particularly in VLSI design, like physical design, like Verilog, VHDL. What is your interest? Semiconductors also is a big, and go for some modeling. Okay, some modeling type of a thing, and try to see what is the like what the industries are working on that. Because after, believe me, after 10 years or might be, the syllabus is going to be changed, and the things are nobody's asking about the transistors, register. Might be it's a basics, it's always required, but everybody's looking for the skills. What you have, you are the teacher if you know the skills, what I believe. Okay, so this is my personal belief. So I'm just suggesting, because you are much might be, as sir told, 3 to 5 years of experience. So just try, if you are doing your PhD also, just try what is going into cutting edge, what is going into the industry. Okay, because the paper publication is also important, but what I believe that you should see, because what product you have, prototypes and all those things you have to see, right? Like biosensors, if you prepare, you have to see physically how we are going to implement, and what type of things. Means focus on the things. Do one thing, but do it completely. Don't put everything in your, like, you know, all the things. It's now, this is not the requirement for the time, what I believe. I think it's okay, sir.
Okay, sir. Sir, one last question, sir. Somebody is asking, what is band-to-band tunneling and how is it exploited in TFET operation?
Yeah, actually, band-to-band tunneling, as I have already told, this is actually what happens. It is happening from conduction band to valence band. Like valence, it depends on the like which type of material you are using. Like I have already have the slide for that one, like this one.
Okay.
Yeah, this is the band-to-band tunneling, sir. This is right. So here, if you see, this is the conduction band, right?
Yes, sir.
This is the conduction band, right? This is the valence band, right?
Yes, sir.
Okay, here also, if you see, this is channel intrinsic, and this is because we have P plus source, N plus drain, and this. So now what happened, generally when we are doing the things, it is going from here. If we are talking about this conventional MOS, But when
Sir.
we are talking about the TFET, in the TFET, the things are going like this. So this is from one band to another band, the tunneling is happening.
Okay.
Tunneling means in between. Tunnel, you know, not tunnel like we are going
Yes,
from
sir.
the tunnel from one place to another. In the
Yes,
mountains,
sir.
we are
Yes.
getting tunnels for the road.
Yes.
Like same
Yes.
here,
Yes.
tunnel is there. So this is the tunneling actually. And this is the quantum phenomena. This is depends on the Schrödinger equations, many things, density of states, empty states are there. That's why it's only possible. And the doping should be very high. Right?
Sir.
Because high doping, the charge is very highly energized. That's why it's only transfer, else it's not possible. Like these type of things are there.
Okay, sir. Sir, another last basic question, sir.
Yes, sir.
What are the limitations of conventional MOSFETs than TFETs in low power applications?
Low power applications, limitations, if we are saying, sir, like as already I told that the conventional TFET is basically, conventional FET is thermionic emissions. Means if we are talking about conventional FET, it needs this much of energy. Like suppose this is the ball and you have to cross the ball to the mountain. What you have to put the too much force. Then the only means the voltage is too much. You have to give the current, the speed also. Then it's only possible. But when we are talking about the TFET, so it is like this. We are just putting light force. No need for just we are means the mechanism of the transferring is totally different. One, we are making the tunnel in the mountain. Another one, we are crossing the mountain by putting the force. Simple thing.
Okay, sir. Okay,
you understand? Like this is a very simple under what I try to like, and this if he wants like, and the major thing is like the switching speed of the tunnel FET is very good comparable to the MOSFET. Like on to off ratio, on to off ratio, off to on ratio. Right? This is because we are getting less than 60 millivolt per decade because of because here we have na KT by Q. If you calculate this, this is VT. Then there is a 1 plus CD by CG. If we calculate this whole value by the conventionals, we are getting in the case of MOSFET this much. But when we are going with this, this is approximation is not valid for the TFET. Right? Because we are not getting this VT. This is the like some basic idea I have given. Else, if the detail we will explain, no problem, because it requires somehow the time. So it's
okay, sir. Okay, sir.
Yeah.
Thank you, sir. Thank you. Any other questions from participants? I hope.
Sir, one more last question, sir.
Please,
sir, are there any free tools, sir, other than the Silvaco?
The Nano Hub you can try. Nano Hub you can try. Nano Hub is the free one. This is the online tool. One of my friend, he did his PhD on Nano Hub. He not used any tool. He did everything on Nano.
Sir, can we start research on that Nano Hub, sir?
Yeah. You can, sir. There are a lot of the tutorials are there. Nano Hub. Okay, this is the online free website is there, so you can start many things on this.
Okay. That means the TFET and
even you can
all those
you can give the laboratory to the BTech students, MTech students. It's good.
Okay. Very good.
For the Nano Hub, everything is there. Tutorials are there. Nano Hub, just you put on Google, you will get the things for solar cells, everything.
Okay, sir. Okay, thank you.
And the crack is also available, sir. For Silvaco ticket, crack is available.
Crack is on the Silvaco, sir.
Yeah, crack is available, sir. If you just put on Google, you will get it.
Oh, okay, sir. One more thing, sir. You said one of the books, sir. Let me share that link of the book, sir.
Link of the book, sir. I will.
If it is possible, we just share to this Srinivas, sir. It's very much useful to us, sir.
Yeah, I will share, sir. It's easy, sir. It's even the lectures are there for that particular professor. See with this. Just you put MOS transistor. You put even the lectures are coming. Operation and modeling of the MOS transistor.
Okay.
Yeah, this is the book. Very good book, sir. Okay, so Yanis Sedvidis. This is very good book. Even for the semiconductors, if you are looking, I think everybody is using Donald Newman. But there is a one more book, Bishwas Newman. That is very good book. Small book. Bishwas sir is Dhupesh Bishwas. He is from IIT Kharagpur. And Donald Newman. Very small book and very for semiconductors. Like we are looking for the big books now, so very small. And MOS transistor, this book is very good. Many books are there, sir. For an analog, you know, Razavi and all. Everybody knows. If you put on the Google, you will get it.
Okay. Thank you very much, sir.
Most welcome, sir.
Okay, sir. Thank you. Thank you so much.
I think it's okay,
sir, before we close, our co-coordinator would like to thank you. Madam.
Thank you, sir.
So thank you, sir. Thank you for the wonderful session and for sharing your valuable insights with us. We look forward again to have you in the future, sir. Thank you.
Anytime, please. Thank you.
Yes, sir. Yes, sir. That's what I am also going to say. We will make you part of our future programs.
Anytime, sir. I'm always available.
Okay. In the chat, participants are asking whether to share this PPT with them or not. If you permit, if you can.
I will. You can, sir. I will share also with you. No problem. It's not.
Okay, sir. You can share to me. I will share to them in the chat box.
Okay, sir. Okay, sir. No problem. Yes,
Okay,
I will
sir.
share it because it's around 30 MB of a file. I will share later on. Later on, you can share with them.
Yes, sir.
So
Yes,
sorry
sir.
to disturb you, sir.
Yes, sir.
Okay, ma'am.
If you are
Okay,
able
proceed.
to provide the link of Silvaco cracked version, can you please?
Sir, see, officially I can't do that one. Might be personally you can reach the sir. I will give it to you. Okay, please.
Okay, sir. Okay.
Yeah.
Okay, sir. Okay, thank you, sir.
Most welcome, sir.
Okay, sir. Thank you so much once again for your excellent session to start with our FDP. And we will cherish it for the next 6 days also. I hope the participants are also very much satisfied and they have asked some questions also. They're asking, they're asking you to learn from you what are the tools that you are using for your research and what are the books
Even
that are
sir,
being followed.
If there is some other thing or might be here, I will also want to give some insights of the FET-based sensors like photo sensors, gas sensors. Even I will share the codes also, no problem. So we will see in the later on, might be anytime.
Okay, sir. Okay, sir. Definitely, sir. We will make you part of it.
Okay, sir. Thank you, sir.
Okay. Thank you so much, sir. Thank you.
Most welcome.
Thank you, sir.
Okay.
Thank you.
Second session, now we will be having from Dr. Shikhar Gupta, who is a staff engineer from Synopsys India Private Limited, Bangalore. Shikhar ji.
Sir, I have made him a presenter.
Sir, please unmute. Shikhar ji. Madam, just wait. I am calling sir. He has already joined,
Okay,
it seems.
Okay, sir.
Shikhar ji, am I audible? Sir, I can see your mic is on, but your voice is not audible to us. Shikhar ji, please check your microphone. You are not audible. Please log out and then log in again. That may solve the issue, please. Arpita ma'am.
Sir.
Please look into the attendees list and make Shikhar sir as presenter.
I've already made him a presenter, sir.
No, he has logged out and going to join again.
Okay.
Because there is an issue with his microphone.
Okay, sir.
Sir, am I audible? Shikhar sir?
Yes, sir. Audible, sir.
It's okay, ma'am. I'm asking resource person. He has joined. Shikhar sir, you are not audible. Arpita ma'am, make him presenter first.
Sir, I have made him presenter just now.
just now, but he is not able to be seen in the presenters
Sorry,
list.
sorry, left, sir, just now left. We make his make presenter.
Okay, Shikharji, join again. Shikharji, please join again. You are not able to be seen in the list. Dear participants, please hold on. We are following up with the resource person. I think he has some problem with his microphone of laptop. Shekhar sir, please do one thing. You share your PPT to my WhatsApp and you join through mobile. We will operate the PPT.
Hello, sir. Am I audible, sir?
Right now you are audible, sir. Fine.
Yeah.
Fine.
Sorry for
fine.
the inconvenience. There is some mic issue at my laptop.
Okay, no problem. Arpita ma'am, please make him presenter now.
I have made him a presenter, sir. Now.
Shekharji, now you can share your screen.
Yes, sir.
Okay, Arpita ma'am, meanwhile, you please introduce sir by projecting the session 2 slide once.
Yes, sir. I hope it's visible, sir.
Okay, it is visible and you are audible too. Please go ahead.
We are honored to have with us today the distinguished speaker of session 2, Dr. Shikhar Gupta, sir, Staff Engineer, Analog Design, Synopsys India Private Limited, Bengaluru. It's my privilege to briefly introduce Dr. Shikhar Gupta, sir. He's currently working as Staff Engineer, Analog Design in IPG Interface, PHY team at Synopsys India Private Limited, Bengaluru. He has over 10 years of research and industry experience in the field of VLSI design. He has obtained his PG degree in VLSI design from JC Bose, UST YMCA, Faridabad, and PhD from NIT Kurukshetra. His research is on spacer engineered advanced underlap MOSFETs. He published 12 articles in SCI journals and conferences. He has in-depth knowledge of programming languages like VHDL, Perl, and software tool proficiency like Synopsys, CentOS, TCAD, Synopsys Custom Compiler, Cadence Virtuoso for digital and analog circuit design, and layout design, Xilinx, and LT Spice. I hope his expertise will surely enrich our learning component and wish to have a fruitful session ahead. Shikhar sir, please share the presentation and continue with the session, sir. Sir, am I audible?
Yes, ma'am. You are audible.
Yes.
The screen is up. Hope.
Yeah, it is visible, sir.
Yeah. Thank you, ma'am, for the brief introduction. So, hello, everyone. This is Shikhar Gupta. I'm currently working as a staff engineer in Synopsys Bangalore Private Limited, Bengaluru. I am there with the organization from last 3 years, since June 2022. Before that, I did my PhD from NIT Kurukshetra, and Professor Rao was my colleague over there. So we had a very great time, and I think with this session we build up more friendship between us. And I did my PG from YMCA University of Science and Technology, Faridabad, and graduation from a government college, Bharatpur. Moving ahead, my topic of presentation is the spacer-based advanced MOSFET. So as we know that the MOSFET, the evolution of MOSFET, so in the early 1950s, the MOSFET was discovered, and in the Bell laboratories, And the first integrated circuit was discovered in the 1958 to 1960 at the Texas Instruments. So at that time, this is the early days of the integrated circuits where the only few number of transistors being there in a single IC. When then the next era come in between the 1960 to 1970, where which we call generally as a medium scale integration. So at that time, we are able to make up to 100 transistor on a single chip, and this chip was sometimes used for the radio communications and microcontrollers. And radio communications means that at that time we have a space exploration all over the world going on in USA, USSR, all over the world. They are busy with the space exploration. So these chips were used over there at that time. Furthermore, in during the 1970s to uh, is there any question from the audience? Okay,
Sir,
I'm
please
moving
go
ahead.
ahead.
Yeah.
It is a slight
No, sir, please
microphone
continue.
disturbance.
Yeah. So from the era of 1970 to 1980s, that since there is a huge demand to scaling down the device sizes and increasing the MOS transistors over a single chip, that lead to enhance the fabricate a MOS chip up to 1,000 in a single IC. So that ICB is used in the microprocessors like Intel 4004, 8080 microprocessors, as many of us heard about it. Now in the modern era, we have a millions of transistors from 1 lakh to 10 lakh at the SoC level, and these are used everywhere around nowadays in the wireless, in the communication, in the CPUs, GPUs, robotics, everywhere in the AI accelerator, everywhere we are using these ICs. So let me go to the some basic background of the MOSFET. So MOSFET, conventionally MOSFET that were initially fabricated at the time of at the Bell Laboratories in 1958 around, is the four-terminal MOS structure. So they're namely called as the source, gate, drain, and the bulk. So which is generally used as an electronic switch to turn on and turn off using the gate as a main active element to turn on the device and turn off the devices. When source and drain is responsible for the flow of the current, or you can consider the flow of the electron. The electron is being passed from the source to the drain. So this flow of the electrons from source to drain is directly controlled by the gate. And also in 1965, the co-founder of the Intel, Gordon Moore, has discovered that every 2 years, around of 2 years, the number of devices on an IC is increased by that 2. So we have already seen earlier that the era up to 1960, there is all around 10 ICs. From 1960 to 70s, there are up to 100 transistor in the IC. From there, from 1970 to 80s, there are around 1,000. Then later, it is up to millions. So that Gordon Moore has predicted, which is called as a Moore's law. It means that every in the period of 18 to 24 months, the number of devices in an IC is going to be double. So which lead to a one very important phenomena to scale down the channel length. So previously we have a channel length of up to the micron, or initial days it is up to the level of a milli. Now we move to the micron. Now we are scaling the channel length up to the nanoscale level. While scaling the channel length, there is always the benefit of disguise. You can consider the short channel effect. So short channel effect means when we are going to scale down the device sizes, there is the more that there is electric field from the gate to the drain will impact the drain current. Electric field from the bulk to the gate to the bulk is going to impact the leakage current. Also, electric field from the gate to the source and the gate to the drain, which is causing the parasitic capacitance. So parasitic will going to the impact, and with increase in the parasitic capacitance, the gain of the MOSFET, which is used as in the amplifier or op amp, is also going to the impact. So to deal with this short channel effect in the conventional MOSFET, in the nanometer is regime, non-conventional MOSFET are being introduced by the scientists. So in conventional MOSFET, there is only a channel is regulated by the gate from the top only. So there is a huge risk of control of charge at the surface of the channel. So since gate is at the top and the bulk is at the bottom, so gate is not able to sometimes control the bulk area also. And since sometimes charges are so deep in the channels that there are many carriers flowing from the gate to the bulk and drain to the bulk, which causes the leakages also. Further, to enhance the performance, the gate control of the mobile charges carries present in the channel length must be enhanced. Means that if we have a better control of the whatever the electron flowing from the source to drain, how much the control we have totally impact the performance. If we have a very good control over the flow of the electrons from the source to the drain, we have a better control of the output, and ultimately whatever, whether the MOS is used in an inverter or in an op amp, the delays, the margins will going to be impact, the gain bandwidth product, the frequency response going to the impact. So with these limitations, researchers are moving with non-conventional devices like multi-gate MOSFETs. So multi-gate MOSFETs, that channel is not controlled by the gate from the top side, but there is some other area where we can place the gate. So the figure depicate that the A is a conventional MOSFET, where the source and the drain and the gate, and the red region over here is the channel region. So whatever the flow of the current from the flow of electrons from the source to the drain is directly controlled by the gate only. So there is no reason to control this flow. Then later we have a double gate MOSFET structure. It means that that channel region is sandwiched by the gate. So there are two gates. The B depicts that one. So there are two gates. So gate is going to control the channel from the two directions. So since there is more electric control, electrostatic integrity will be more at the channel region. So there will be more current, and ultimately if the current is more, so everything will be more. You have a less delay, you have a more gain. Then furthermore, we have a FinFET structure, which is the C1. So FinFET structure, so the channel region is considered as a fin, and the gate is surrounded by that channel. So that is a fin. So the only difference is that there is a oxide layer in between the gate from the channel. So that oxide region, that the top portion, that thickness, gate oxide thickness is more rather than the side gate oxide thickness. So which comes to the invention of the tri-gate FinFET. So tri-gate FinFET, that gate oxide thickness from the top is lesser than the FinFET structure, which will lead to enhancing the gate control of the channel from the top as well. Since electrostatic integrity is more, so the MOS family has only one concept, that if you have a good electrostatic integrity means you have a good control over the good control in the channel region. If you have a good control of that channel region, the device will perform a very better way. So in the tri-gate FinFET, we have introduced that, okay, we are going to use the top portion of the gate of the FinFET to control the channel. Furthermore, we have a quad FET, or quad gate fact, where the gate is surrounded by the gate is encased to the total the channel region after the nanowire structure, or you can say the gate all around MOSFET. So it will totally expel the corner electric field, and the gate is totally the channel is totally covered by the gate, and we have a very good electrostatic integrity over the channel region, leading to a much higher performance rather than the other device technologies. Moving ahead to the underlap devices. So since we already see that use of the double gate or tri-gate or the gate all-round structure, which lead to the good electrostatic control of the uh, good electrostatic control by in the channel region. But since the electrostatic control is more, there is one disguise is that we have is underlap, we have a fringe capacitance is there. So a fringe means we have a electric field lines from the gate to the source is there. From the, if we talk about the double gate, we have electric fringing electric field from the gate to the source, which lead to the parasitic capacitances. So this parasitic capacitances enhances with the advanced MOSFET, which lead to the reduction in the gain when we talk about the analog performance of the MOS. So to uh, to reduce down this, what we can do, we can introduce the spacer. We can use the underlap devices. So underlap devices means there is a physical separation between the gate and the source, so that the electric field from the gate to the source becomes weakened. So it will reduce, it will not, it will reduce the parasitic capacitance, that the fringing field will be weakened, then the parasitic capacitance is also going to weak, and in this manner, and also there is no impact on the gate to channel control. The gate to channel control remains same, but the gate impact of the gate electric field over the source region and impact of the gate electric field over the drain region is going to be less, which will lead to the maintaining the same gate current flow, same flow of the electrons from the source and the channel, but reducing down the parasitics from gate to the source and gate to the drain. So this source drain extension doping profile is introduced to optimize the value of the underlap length. So we have to first, we can't take the underlap length as much as possible as our wish. We have to optimize. So optimize in this manner that the impact over the gate control in the channel region and the impact of the drain current from so drain to source is not going to, is not being effective. And it also, with introducing of the underlap devices, it going to enhance the circuit deterioration and dynamic power of the devices. Is it also going to improve the self-heating effect, as I already told that parasitic capacitances, however, to reduces, and the device becomes more appropriated thermally stable with this type of a structure. As junction capacitance is also reduces, it will also going to enhance the analog performance in terms of the gain bandwidth product. So these are the benefits. One of the major contribution of the underlap in the double gate or the advanced MOSFET family, especially in the FinFET structure. So what is the impact of the fringe capacitances? So fringe capacitances is that there are two type of fringe capacitances. Whatever the electric field from the gate to the source and the gate to the drain, these are the fringing electric fields. So the fringing electric fields are, as I told you earlier, that it is responsible to generate the coupling capacitance between the source and the gate and the source and the gate and the drain. So these are the two electric field, that one is the outer fringe electric field, one is the inner fringe electric field. So based on those, we have a parasitic capacitance of outer fringe electric field capacitance and inner fringe electric field capacitances. So this, if we optimize the underlap length, then this electric field will be reduced, and this capacitances will also going to be reduced, which ultimately enhance the analog performance of the devices. So in this electric field, what we have going to fail, we are conventionally we are using dielectric like silicon nitride and silicon dioxide. If we are going to use the air or vacuum in this dielectric, so since the air has the least dielectric of 1, so if we are going to use the dielectric air as a dielectric in this region, so this portion is also that our COF, whatever the outer fringe electric field capacity, parasitic capacitance, this is going to be reduced as low as possible. So that I will explain later in the slide. So use of high K spacer in the undoped underlap region of the FinFET, the effect of the gate induced fringe barrier lowering, which ultimately improve the performance of the device and the circuits. High K spacer underlap MOSFET enhances the figure of merit in terms of the gain bandwidth product, cutoff frequency, and the gate fringe electric field enhances the with the use of high K spacer in the electric field. So as we know, as we increase on the technology, we can't maintain the same gate oxide thickness. So there is a term called as effective oxide thickness. So to use the effective oxide thickness, that we can't use a silicon dioxide of 1 nanometer or 2 nanometer. It is very difficult to fabricate the silicon dioxide of that that small thickness. So we use the term electro oxide thickness. It means we are using a high K dielectric spacer. So in this manner, if we are using a high K dielectric, we can have a benefit of high gate oxide thickness. So with the use of the spacer dielectric, that we can have a high K dielectric, and with that we can improve the performance of the device. Also, we can use a dual K spacer. Dual K spacer means the one of the portion of the sidewall spacer of any high K dielectric, and other half is of the low K dielectric. So it totally based on how the performance is going to be impacted. So in general convention, that whatever the dielectric near to the gate wall, it should be the high K, and whatever the dielectric near to the source or drain, it should be the low K. So dual K spacer will going to limit the short channel effect in a very significant manner. Also, the symmetric dual K spacer enhance the electrostatic integrity over the channel region, which lead to the enhanced noise margin, delay performance also. In tri-gate FinFET, source side of the dual K has a good gate control, which ultimately reduce the transconductance and the output conductance of the devices. So let's talk about the air spacer. Gate side air spacer in the MOSFET. Okay, let me go back to this diagram. Okay, so air spacer means we are introducing. So this is the underlap region. So we can use a high K spacer over there, we can use a low K spacer over there, and we can use a dual K spacer there. So whatever the fringe capacitance we are over here is going to defined by the whatever the spacer dielectric we are using in this region. So if we use the air as a side spacer dielectric in this underlap region, and with the optimized underlap plan, then we have a benefit that this fringe capacitance, outer fringe capacitance, which is a parasitic capacitance, is going to be 1. So this benefit we can use to enhance the power, enhance the performance in terms of the gain and the cutoff frequency. And this device, this type of device being easily used for the high frequency operations. So moving to the AI spacer, that gate side spacer structure in MOSFET reduce the gate fringe capacitances, which result in the low power dissipation and high speed of operation. Okay, high K dielectric, whatever high K, what is the impact of the high K? We use high K spacer dielectric instead of the low K spacer dielectric. So as I told you earlier, that the high K spacer dielectric, the fringe capacitances are more rather than the low K spacer dielectric. So with the low K spacer dielectric, this parasitic capacitance is reduces, we reduce the power consumption, and since the device capacitances are also going to reduce, the speed and the switching time is going to be reduced as much as low as possible. So in the MOS family, we majorly focused on the speed. The speed should be as high as possible. The switching time should be as high as possible. The delay should be as low as possible. The power consumption should be low as possible. So with the optimized underlap length and the use of air space in the underlap region, we can achieve this these 3-4 merits in the advanced MOS families. So air spacer or vacuum spacer is one of the prominent candidate to reducing the device capacitances when vacuum is used as a space instead of the conventional MOS family, which is the silicon nitride. That gate control over the channel air region is enhanced. And this enhancement we can observe for the fixed EOT. The EOT means effective oxide thickness. So varying the gate space, varying the gate underlap spacer dielectric for a optimized FinFET structure, there is a very small variation in the drive current. There is a fact that if we are using the spacer as a underlap in the underlap dielectric in the sidewall region, there is huge possibility of the reducing of the gate current. But with optimized underlap length, we can maintain the same current level while reducing down the parasitic capacitances. So these are the formation of the spacer. So this is being presented in one of the IEEE paper EDL by Dr. Angada Sachet, which is under the supervision of Dr. Changming Kevin, who is the father of the FinFET. They have created the AI spacer based MOSFET in coordination with the IBM labs. I'm not exactly remembering, in coordination with the IBM labs in the 2016, 15, 16. So this is the engaged gap structure. With this technique, we can form the AI spacer. So after etching of the gate stack and ion plantation of lightly doped source and drain region, that carbon is selectively deposited. So there is a selective deposition of carbon. This is the purple which you are seeing is the carbon. So this carbon is deposited over this structure. And the red one is the gate, and the blue and blue is the source and drain. So there is a little bit underlap region, this one. So that carbon is selectively deposited at the side wall of the gate using the ion beam method. Then with the deposition of carbon, the silicon is deposited all over the place, and then silicon is when the silicon is deposited, it will react with the carbon, and when the silicon is all over the place, then this is already attached to the carbon which is deposited at the gate side wall. With the mild oxygen plasma, this carbon can be removed, leading to the air gap structure over there. So when with the oxygen plasma, the carbon is reacted with the oxygen, forming the CO2, and the CO2 is wet dropped from the structure. So there is a hollow structure, or you can consider there is a vacuum over this structure, which this vacuum is being spaced from the source to the gate and drain to the gate. Finally, the ion using the ion implantation method and the thermal annealing, we can activate the dopant and the gate sidewall spacer, air spacer being introduced over there. So in my research in the NIT Kurukshetra, I have tried to do this in the various device technologies like tri-gate FinFET, tunnel FET, gate all-round, and using this structure in the one of the analog circuit and to check the performance of the spacer in the underlap region. So one of the result I'm going to present over here is the effect of air spacer in the tri-gate based FinFET. So we are going to use spacer, different type of spacer, silicon nitride, silicon dioxide, and air as a gate sidewall spacer dielectric, and check the performance of one of its kind. So I'm going to show only the two results of silicon nitride and the air, because the silicon dioxide results is in between the silicon nitride and the air. So while keeping the EOT of 3 nanometer or 0.65 nanometer, we can see that there is a very slightly deviation in the channel region of slightly deviation of the conduction band energy in the channel region. So this is that portion, that there is a very slightly deviation of the conduction band energy in the channel region if we use air as a spacer dielectric at lower EOT. So since there is a very less deviation in the conduction energy, so the current will be current flowing from the drain to source will be same. So since current is going to be same, so there is a very limited impact over the threshold voltage. And since threshold voltage is not going to change with the use of the air as a dielectric spacer, the intrinsic gain of the device is almost same. So the transconductance energy generation efficiency, the TGE, which is mimicked by the GM by ID ratio. In generally, the scholars use this term, represent the strength of this device to amplify the signal up to a certain extent. To estimate the efficiency of the device, it converts DC power into the AC frequency and gain. So it is seen that for at lower EOT of 0.6, there is a slightly deviation of the EOT. So slightly deviation of the GM by ID ratio. Since GM by ID ratio is almost same, so there will be a very low or very less change in the gain. But since there is a huge impact on the parasitic capacitance, the parasitic capacitance is going to be increased, going to be reduced, then there is a huge impact on the gain. That parasitic capacitance reduces, then cutoff frequency is increases, then gain bandwidth product is ultimately going to increase, which lead to the better performance of the device for the analog performance. So use of the air spacer as a spacer dielectric in the optimized underlap length, we can achieve a better analog performance of the device. Also, we have to optimize as I told you earlier, we have to optimize the underlap length. So we have some optimization result. With the optimized underlap length, there is a very less impact over the conduction band energy. So since conduction band energy is very high, less impacted, so there is less impact over the gain, but the capacitance is going to be reduced with the use of air spacer. Then we can achieve a good performance for the cutoff frequency and the frequency component and the gain. So this one of the benefit we have used, we can use for the AI spacer. Although the fabrication process, which I showed you here earlier, is quite expensive, but this technology is being used with to reduce down the parasitic capacitances. So if you have any query on that, please raise your concern.
Participants, any queries so far? Any questions, please? Okay, sir. If they have any questions, they are posting in the chat box. We will look into it during the last part of the session. Meanwhile, you continue.
Okay.
Okay.
Sir, your screen is not visible, sir.
Just a minute, ma'am. Just a minute.
Okay, okay, sir. Okay, sir.
So let's move ahead with the impact of spacer in the underlap region of the tunnel fat. So in this, I have used a dual case spacer, as I explained it earlier. That dual case spacer is we are using the two type of gate sidewall spacer dielectric. One is the high K, one is the low K. So dual case spacer be used in the tunnel fat. So this is the basic double gate tunnel fat. The source is N plus and the drain is P plus. So dual drain is P plus, and I am using a high K spacer towards the gate side and low K spacer towards the paddock side, or you can consider the source and the drain side. So the use of low K spacer, I have experimented that use of a low K. I have simulated different type of low K material in the dual K for the dual K spacer, like silicon nitride, silicon dioxide, and finally with the air as a low K spacer dielectric. Since we already see that use of the air as a spacer dielectric in the underlap region, it will going to reduce down the uh, reduce down the impact of the parasitic capacitances. But why we are using the 12K spacer, especially for the tunnel fat, there is a very less amount of the current. So if we are going to use a space completely air as a underlap completely air spacer as a underlap spacer, there is a huge reverse impact of the drain current. The drain current is going to be reduced more. So to maintain the drain current flow, we have used the high K spacer. So okay, let's go ahead with the basic tunnel fat phenomena. So tunneling path, it is a physical path, equipotential path between the conduction band and the valence band. So these are the tunneling path. So it should be as low as possible. The device will be as good as beneficiary. So if we are using, so these are the some simulated results. If we are going to use air as a spacer dielectric in the outer dual case spacer region. So the tunneling length will be reduced. So since the tunneling length is going to reduce, there is because of this, the tunneling length is going to reduce electric field in the tunneling region is going to be increased. So with this increase, the GBTBT is going to increase, and finally the tunneling current is going to be increased. So in this manner, we have seen that use of low K spacer in the dual K spacer region in the underlap based FinFET, the tunneling per length can be reduced, leading to increase in the current. Also, when the current is going to increase, one of the important factor in the tunnel FET is the subthreshold swing. So with that, the subthreshold swing is also going to be reduced. And finally, if we check the performance of the drain current, the drain current performance is going to be increased, as we know that current is going to be increased. So in this, this is a asymmetric tunnel FET. Here the source has a higher doping concentration and drain has the lesser doping concentration. Why we are using the asymmetric doping? To reduce down the ambipolarity. So what is the ambipolarity? Ambipolarity is like this. If see, we reduce down the gate voltage, the current is reducing, but at particular time, after a particular voltage, the current is again increasing. So this is called ambipolarity. So ambipolarity means that device is ambipolar. It can be worked either as the source can be worked as a source or a drain. Similarly, drain can be worked as a drain or the source. So this is ambipolarity. So to reduce down the impact of the ambipolarity, we have the asymmetric doping structure. So with that, I have seen the performance of the spacer dielectric, that this is the gate transconductance. This is the right side is the transconductance, left side is the output conductance. So that transconductance of the device is enhanced with the use of the dual case spacer, and also it further enhanced if we use as a air as a outer case spacer in the dual case spacer region. Since transconductance increases, also the drain output conductance is reduces with the dual case spacer, the gain of the device is going to be increased. As you can see that in the right side of the graph, the left x-axis is left y-axis is the gain, and the right y-axis is the frequency. So the use of the dual K spacer, it will reduce the capacitances, ultimately reduce all the parasitic capacitances, uh, which lead to enhance in the frequency response of the devices. So this frequency response, this is the cutoff frequency, which is generally considered as the unity gain frequency, is going to increase, and the Fmax, which we can generally consider as the unity power gain frequency, and other frequency component, transconductance frequency product, gain frequency product, gain transconductance frequency product, all this frequency component are going to be increased with the use of the dual case spacer, and also it's going to increase with the use of the air as a outer K material in the dual case spacer region of the tunnel FET. So let's talk about what is the impact of the underlap region, what is the impact of the spacer dielectric in the underlap region in the gate all around structure. So the top one is the 3D view, later one is the 2D view of the gate all around silicon nanowire structure. So here the gate is, the channel is totally surrounded by the gate, and this is the light brown is the gate, and the dark brown you can consider the gate oxide. So since the channel is totally surrounded by the gate, there is a huge control of the flow of the charge carrier across source to drain is controlled by the gate. Since there is a huge electrostatic integrity, the drain current will be more compared to the other MOS family devices, and the since drain current is more, the delay will be less, the switching will be more, the gain will be more. So if we check for a particular EOT, I have varied the EOT from 0.6 to 0.1.2 for air spacer and the nitride spacer base. So if at lower EOT, because when we scale down the device sizes up to the 3 nanometer, 4 nanometer, the lesser gate oxide thickness is more beneficiary. It means gate oxide thickness, not the physical one, but the effective one. So EOT is the effective gate oxide thickness. So whatever the lesser effective oxide thickness is more beneficiary. So at lower EOT, if we use air as a spacer dielectric and silicon nitride as a when compared with the silicon nitride, there is a very few millivolt, a very less number of conduction band energy deviation. If you see, this is the conduction band energy. So there is a very less deviation in the energy in the channel region. So since there is very less deviation in the energy, also since it is a gate all-round structure, the gate is surrounded by the channel is surrounded by the gate. So there is almost negligible impact of the air as a dielectric space, gate sidewall dielectric spacer over the impact of the drain current. And this is mimicked over there, that transconductance generation efficiency is more in air spacer based device rather than the silicon nitride spacer based device, leading to increase in the current, leading to increase in the gain and the frequency component. Frequency component is also going to also very beneficiary when we talked about the air as a spacer dielectric, because the parasitic spacer is going to be reduced with the use of the air as a spacer dielectric, and also we are increasing the transconductance of the device. So the frequency is also going to be increased. Frequency response is also going to be increased. The other frequency response, the power gain frequency, transconductance frequency product, other frequency product is also going to be enhanced with the use of the air as a gate sidewall spacer dielectric. So this is okay, one of the major application of the MOS, because we are not going to use the MOSFET at the ambient temperature. We have to use at the low temperature, and we are going to use at the cryogenic temperature to the high temperature also. So here I have seen the variation of the temperature response with the use of the air, because air is spacer. Because these device can be used at the higher temperature or can be used at the lower temperature. So with the use of if we reduce down the temperature, the transconductance generation efficiency will be increased. So it means there is more current flow. It means there is the more impact on the gain, if because of the high transconductance and the low output conductance. And the capacitances also, there is a very marginal change in the capacitances. So capacitances is not going to impact that much over the performance of the device if we are going to use air as a spacer dielectric, and that device is used at the low temperature regime. So these are the variation of the low temperature with using the device at a low temperature. We have a huge gain. We have a huge gain. We have a less capacitances. We have a huge frequency responses, and other frequency responses in terms of power and the transconductance is also going to be increased. So this type of devices, like a dual K spacer where outer K is low K spacer dielectric, especially with the air spacer, or fully air spacer based underlap devices, which this type of devices can be used at the low temperature as well. So these are one of some publication which I have presented for different journals while making the results for the use of air as a spacer dielectric. That's all from my side. Any questions from the audience?
Okay, dear participants, you can ask if you have any questions, please.
Excuse me, sir.
Yes, sir.
What are the main advantages of GAA SNWT FET or device?
Yeah, thank you for bringing this one. So as we know that technology is rapidly increasing. So previously we have moved from BJT to MOS, so MOS to double gate. So the idea is scaling is we have a better gain. We need a better gain. We need a better switching. So this can be achieved if we have a good control over the channel region. The good control of the channel region can be achieved by covering the channel from the gate. So this can be possible as much as, so gate all around structure has uh, all the channel region is surrounded by the gate only. So let me show the screen again.
Okay, sir.
So the F structure. So here the gate is the channel is surrounded by the gate from all the directions. So we have possibly achieve all the possible way to control the channel. So if we have a control of the channel, so we have a very good control for the switching. Ultimately, MOS totally depend on the how good switch it is, how rapidly it will switch. If we have that, switching is totally depend on how good we are for the gate control. So the gate is totally please.
Sir. Yes, sir. Please
Yeah.
continue.
Yeah, so the channel is totally surrounded by the gate. So see, it is a, if we imagine the 3D structure, so consider our finger as a channel, and if we want to cover our finger, there is only four all the directions like in a cylindrical form. So this is the benefit of the gate all-around structure. So we have a huge control of the, there is no huge control over the gate, and since control over the gate is enhanced, the switching will be enhanced, the uh, uh, gate drain current will be more, the frequency response, the gain, the delay, these will be enhanced. So this is one of major benefit. Now companies are also targeting to achieve the to create the gate all around structure, so that this can be used in future with maintaining, not going beyond the some micron, beyond the sub nanometer regime, but maintaining the sub nanometer regime, achieving a high performance with the gate all around structure.
Sir, 1 second, sir. What is the present status of usage of this particular GAA SNWT device? Present status.
So presently, presently Intel are using quad FET. Intel give the terminology omega FET, and gate all-round structure is given by the TSMC. So they have modeled their one of their PDK for the omega FET or the gate all around structure FET. But commercially, this technology is not there. This technology is still under development. Commercially, we are still at the FinFET level. But since we can't, yeah, please.
As per the literature survey, in 2018 itself, I think this device related literature is available from 2018 onwards.
Yes, sir, not 2018. This structure is way back earlier.
Okay.
The first patent is in 2015 that I saw. That is a cylindrical FET nanowire. You have seen the name nanowire. So there are a few patents of the nanowire that I've seen in the 2016, 2015. So, but that the beauty of that VLSI industry is that we think about for the present day, what we are working at the device level at the present day, it is going to be mimic at the industry after a decade, maybe after a decade or more, because we have to do a lot of rigorous analysis, how it is going to impact at each level, and then after the model development is there. That's why that FinFET was introduced in 2000 by Chan and Kelvin, who when they have named the term FinFET. That was in the 2000. But FinFET technology comes into existence for the consumer electronics. I'm not talking about the research point of view, but what is the end product is the consumer. Whatever the mobile you are using, laptop we are using, TV, any automotive products, microprocessor, controller, the end user or the directly to the industry, it is going to be used after around 20 years.
Okay, sir.
So these technologies are under development. They are still working on. They have some models of the GAA, but commercially the GAA is not as we are focusing. Commercially, the FinFET structure is there by the TSMCs and the other PDK, other foundries.
Okay, okay, sir. Thank you, sir.
Hi, sir. I'm Murali, sir.
Yes, sir.
Sir, let me know some of the tools other than the synopsis to do the research, sir. Because that is very costly tool, I think, synopsis. If any researcher want to start the research on that, it's not affordable. Is there any other sources?
Yeah, so that I already have seen the last few minutes of your Professor Avatar. He already told that if we won't have the licensed of Synopsys or the other tools, we can use the open source. So Nano Hub, there is a site over there. I have seen few years back, few bunch of good people have created a open source. So you can reach out the Nano Hub, and over there is a ticket tool. I'm not exactly recalling the name, but there is a ticket tube. I think the same that Professor Avatar Singh has told you earlier in the session. And if you want to use that tool, then you can do. Otherwise, that is for the simulation purpose. And if you are good in the mathematical modeling, then you need only the MATLAB and any mathematical modeling simulator. So mathematical modeling, just take the model, whatever the of anything that double gate or the FinFET, and you can create the mathematical, you can have the mathematical model and check the performance. That after, if you have the mathematical model, you can see you can directly run the normal transfer characteristics or output characteristics of the MOSFET.
Okay, sir. And one more, sir. Why can't we use the polysilicon layer more than the 16% on the design, sir? Generally, we are using the polysilicon layer for the gate. Why can't we use more than 16% of the polysilicon design? I have seen in some of the book, we don't want to use the more than 16% of the polysilicon design. Is it possible, sir, or other than any layers are there for that polysilicon?
Polysilicon is also there. Sometimes in some of the ICs they use metals also. Metal is also going to be used, but we can't use that much polysilicon height, because that the gate electrode or whatever the electrode source or drain electrode is at the top of that poly. So if that height is more, so the control over there is more, and also there is a breakdown of the poly. If there is more current is going to flow through the poly, so there is a possibility of the heating and the breakdown of the poly. So we can't, there is some limitations that we can't use that much poly length.
Okay. Thank you.
Any other questions from participants?
Sir, one of the participants asked in the chat box, sir. I am reading that question, sir. Hello.
Yes, sir. Go ahead, please.
Tell us about the tools you used and what circuits were made, or was it is the device level only? This is the question asked by the some of the participants.
Yeah, so the tool I have used, the Centaurus TCAD, I had a licensed version of that one. So I have did the simulation analysis of the double gate, tri-gate, FinFET, gate around structure, and one of the case of temperature analysis of gate all around structure. The circuit I have that operation transconductance amplifier. So the tool who used the OTA, that I used this Centaurus TCAD only to run the operation transconductance amplifier. So we have a we can, just like the spice file, we can write the spice syntax in this similar manner. We can write the any circuit like inverter or SRAM, or in my case I have designed the OTA. So I've used only this, but if you want to use, there is another another way, using the circuit simulator, and for that you need to create just like a machine learning or AI model. Not the AI model, you can consider the machine learning model. In that we have a huge range of VG and VD variation, and we will have the drain gate ID, gate capacitance, drain capacitances, source capacitances. So basic parasitic capacitances we have a ID drain current, and with the very huge variation of IG and VD. So that will be a thousands of simulations. So that data sheet we can use, and that can be used in the circuit simulator, and with the help of the Verilog code. So that information is also available over the Nano Hub. I have seen the long time back over there at that time. But if you have a good server and that CentOS, then you can use a simple inverter, or simple 4T RAM, or simple OTA over there. I use the CentOS simulator only to run the OTA, inverter, and SRAM.
Okay, so, and one more thing, sir. Recently we purchased micro window tool, sir. How so far it will useful for that research, sir? Is it sufficient, or is there any?
Which one, sir? Which one, sir?
Micro window.
Sorry, sir. I have not aware of that one.
Okay.
There are some tools which are perpetual, which have the perpetual license, but I'm not sure how much reliable they are, since most of the audiences are the PhDs and researchers. So I don't want you give your effort over a tool, and when at the time of publication the reviewer take that reliability of that tool is not good enough. So if some tools are very good, like CentOS ticket I have used, so one suggestion I can say, if you got any tool which is a freeware, just do the model calibration before doing any simulation. Model calibration means you can find out any IEEE paper or any patent. Over there, they have reported the performance, transfer performance and output performance at the on-chip level. So once you have a experimental data, tune your model with the experimental data. So if your model is tuned with the experimental, so this I have seen in my case when I'm writing my paper for the gate all around FinFET or nanowire. One of the reviewer asked me that your model is not calibrated. So after that, I spent 3 months to did the calibration, and the calibration means you should have a experimental result that would be in the paper, and that experimental result you have to mimic in the simulation model. So if the simulation model is going to mimic the experimental results, you can clearly say that my model is calibrated, and with that model you can then run any device simulations. In this manner, you have a benefit that you are going to give a section that experimental calibration of 8 to 10 lines. Then reviewer will see, okay, this model is not just like that any other model. It's experimentally calibrated. It's not going to give the false result. So the reliability of the result over the paper will be more.
Okay. Actually, that micro is also perpetual license.
Yeah,
Recently
so
purchased.
yeah, that is perpetual license. So it's okay. You just do the experimental calibration. Just calibrate the model. So once the model is calibrated, you will find to know that okay, this mu you need to consider, this alpha you need to consider, this beta you need to consider, this whatever the parameters you are going to change in the model file, you need to consider that only. With that, you can do further analysis over the device. Suppose you are going to work on the FinFET, so you will easily find easily find a paper which has a experimental result of the FinFET, basic FinFET structure out 22 nanometer or whatever the 48 nanometer, so 65 nanometer. Just do the experimental get the experimental result, do the calibration. Once the model is calibrated, no one is going to ask that I'm not relying on the first model, because you have the experimental result calibrated. And if anyone is going to ask, you can directly show the raw XML file or raw files, and you can directly give the source. This is the source of the experimental result. This is my experimental data. This is the calibrated data from the simulation. You can directly send the raw file. That would be the part of the one of the review process. So once the reviewer come to know that okay, this model, this simulator that the researcher is using is experimentally calibrated with these results, okay, I'm relying on the result now. Then after, they will consider your result in a very positive manner.
Okay.
The chances of accepting the paper in this manner is enhanced. No one is going to ask that this your model is hypothetical. You have a calibration result. Okay, it is not hypothetical. This is already experimented result reported in this paper, whatever the journal it is. Just take those result. This is the experimental result is calibrated. I mimic the experimental result. I'm getting the same result. Now this model used in my whatever the device structure or device enhancement you did in there also.
Okay, sir. Nice to talk to you, sir.
Thank you, sir. Same here.
Okay. Any other questions from participants? Any other questions, please? So, Shekharji, there are two questions from participants. Number one.
Yes, sir.
How do spacers affect the parasitic capacitance of the MOSFET?
Okay, okay. Let me bring the screen up again.
Okay.
Rao sir, screen is visible.
Yes, sir. It is visible. It
Yeah,
is visible.
yeah. So this is the underlap structure. So this left is the source. Okay, left is the source, right is the drain, and this is a gate, and this is the underlap structure. Normally devices, normal MOSFET has that the source is over here. Okay,
Okay. Okay, sir.
just a minute. Let me do one highlight. Is the highlighter is working for you, sir? You can see
Yes.
the highlights.
Yes.
Yeah.
Yes.
So
Yes.
normally what we have devices over here that directly connected to over here. This is the source and these are the drains. Okay. So, but we are using the spacer. So this is the source now. This is the drain now. And this spacer is there. There is a spacer. So this should be filled. This should be filled. So we conventionally earlier we filled because we can't not in general we can't directly attach source electrode to the gate. There will be always a spacer over the gate sidewall boundary there. So these are generally we use earlier as a silicon nitride or silicon dioxide. Conventionally it is silicon nitride. But if we use in silicon nitride air or low-K dielectric instead of silicon nitride, so few things is going to impact. There is fringing line. These fringing lines is gate to source electric field, gate to drain electric field. So this electric field, wherever the electric field is there and two electrode is there, there will be a capacitances, right? So capacitances is EOX by A. Okay. So EOX is ER by E naught permittivity, absolute permittivity, ER relative permittivity. So if the ER is less, then capacitances will be less. So ER is means relative permittivity. The air has the least ER, the one. We can't have less than one. Air or vacuum has the least permittivity. Beyond that, there is no permittivity less than that. So if we are going to use a low K dielectric in this region, so there will be the less parasitic capacitances from gate to source and from the gate to drain. So this since parasitic capacitance is less, so overall capacitance impact from the gate to the device all over the device will be less. So this parasitic capacitance will going to add is the part of the gate to source capacitances and gate to drain capacitances, which ultimately reduce down the overall capacitances of the MOSFET. When the overall capacitance of the MOSFET is going to reduce, then the frequency response, that whatever the frequency that unity gain frequency, current gain frequency, which is GM by CG. So CG is the overall gate capacitance, is the capacitance is seen across the gate. When the gate capacitance is reduced, then the cutoff frequency is going to be increased. So in this manner, the spacer is going to impact the device performance.
Okay, sir. One more question, sir. Probably
Yes,
the
sir.
last, it seems. How does spacer thickness impact the source or drain regions, extension regions?
Yeah, so it is the same extension. We can't increase the thickness as our wish
Okay.
because this electric field is going to impact the drain current also. When we talk about the drain current or the flow of the just a minute, let me erase these. So when we're going to talk about the So the gate electric field, gate to this electric field and this electric field. So it is also going to add on the flow of the charge carriers from the source to drain. So ultimately the drain current is going to increase. If we increase this thing, if we increase the underlap region from this to this, then drain will be here. So this electric field, their impact of this electric field will be less. So this electric field impact will less, then the drain current is also going to reduce. So we have to optimize that we can increase the underlap length without changing, without impacting the drain current. Without impacting the drain current, we can increase the underlap length. If underlap length is increased beyond an extent and the drain current is going to reduce, that is not going to benefit our device. So we have to make a trade-off between the underlap length.
Okay.
Yeah.
Okay, dear participants, any other questions? Shekharji, one last question from my end.
Yes, sir. Yes, sir.
So you are working in Synopsys India.
Yes, sir.
Any suggestion, and you are a doctorate, any suggestion to our junior faculty who are in this? Probably there are quite a few faculty who are having around or less than 5 years of experience, who want to pursue their research. So what is your suggestion out of your experience of both academia and industry?
Okay, so currently AI driven technology is going to take care more.
Okay.
So if anything, if you create a model of a circuit or of a device, and that model is AI driven, that is benefit for your research. That will going to benefit, because conventionally, if we are going to do any circuit simulation or any device layer, device based research, it is not very difficult to get the papers nowadays in the recent times. And for the circuit perspective, if we are pursuing your research in the circuit area, then you should have a test chip at the end of the end of their PhD. If you have a test chip at the completion of the PhD and you have characterized that test chip, that will going to give a huge impact of your PhD. It will give a good, excellent remark over your PhD work. Similarly, for the devices, if you have generated the mathematical model of your device model, and that device model and the mathematical model are aligned along with the experimental result, that will always going to have. If you going and with that, if you are going to add the AI, like AI based simulation, and AI based simulation means you should have a huge data set, huge data to run the AI based model. So if you have that one, so it will also going to work very well. But for the devices, if we are going to, if we calibrated your model with the mathematical and the experimental model, it always going to work. It is not going to fade anywhere, although it is a very old way, but it is also going to work with for the researcher. Since many persons don't have all the tool exposure, so with that, many people have a very limited resources. So with that limited resources, few things all can work, we can work with. So that one of the few things is that mathematical modeling. If that mathematical modeling is going to prove with your simulation result, nobody is going to answer, okay, this is not correct, this is not correct.
Okay. Okay, dear participants, still any questions or shall we wind up? HOD sir?
Yes, Srinivas, we'll wind up for today.
Okay. So before we close, Arpita ma'am,
Sir.
with your closing remarks, please.
Sir. Thank you, sir. Thank you for the wonderful session and for your valuable insights. And we'll look forward again to have the futures. As of our 6-day faculty development program, a moment to express our sincere gratitude to all of you for your active participation and engagement. A heartfelt thanks to our distinguished speakers, Dr. Shrikant Gupta sir and Dr. Avatar Singh sir, for sharing their valuable insights and sparkling thought-provoking discussions. Your expertise has truly enriched today's program. We look forward to seeing you again tomorrow for another day of learning. Until then, thank you once again to all the participants. Thank you,
Okay.
sir.
Thank you.
Okay, Shekhar Gupta
Thank you,
ji.
sir. Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you all.
Thank you. So we shall meet again tomorrow at 6 p.m. for day 2, session 3 and session 4. So dear participants, we can leave, please, and meet again tomorrow. Thank you, Shekhar sir.
Thank you, sir.